How far could you actually travel into space within one lifetime? If you left Earth today, how far could you actually get before your lifetime ran out? Would you barely leave the solar system or travel light years into the unknown? Let's find out just how far a human life can stretch in the vastness of space. Earth's first frontier, low Earth orbit. The low Earth orbit, or LEO, is a region that stretches roughly 160 to 2,000 kilometers above the Earth's surface. For perspective, that's less than 1% of the distance to the Moon. And yet, within this thin layer of near space, humanity has conducted some of its most daring technological feats, the first steps of interplanetary ambition, and the earliest experiments in living beyond our home planet. LEO is more than just a number. It is the baseline of human space travel, the first orbit where we learn how the body reacts to microgravity, how spacecraft behave outside the atmosphere, and how human civilization begins to step beyond Earth. Every astronaut who has ever flown into orbit, every satellite that circles our globe, and every piece of technology designed for space, LEO has been the training ground, the laboratory, and the proving ground. Low Earth orbit is defined primarily by its altitude. It begins roughly 160 kilometers above the Earth's surface, where the thin blue atmosphere begins to fade into the blackness of space, and extends to about 2,000 kilometers, the upper boundary where orbital decay slows, and higher orbital regimes like medium Earth orbit, MEO, and geostationary orbit take over. Objects in LEO travel incredibly fast. To remain in orbit, a spacecraft must maintain speeds of approximately 7.8 kilometers per second. That's over 28,000 kilometers per hour, or enough to circle the entire Earth in about 90 minutes. One moment, you are over the Atlantic Ocean. 90 minutes later, over the Pacific. This speed, combined with Earth's gravity, creates a delicate balance. The spacecraft is constantly falling toward Earth, but because of its horizontal velocity, it keeps missing the surface. LEO is where Earth looks small, fragile, and awe-inspiring. Astronauts in this region experience the curvature of the planet, the thin veil of atmosphere separating us from the void, and a perspective that forever alters human consciousness. But before any of this was possible, humanity had to take the first leap into orbit. The human spaceflight begins in the Cold War era, a time of competition, risk, and unprecedented technological innovation. On April 12, 1961, Soviet cosmonaut Yuri Gagarin became the first human to enter space aboard Vostok 1. Gagarin's mission lasted just 108 minutes, but in that brief period, he circled the Earth once, traveling at 27,400 kilometers per hour, reaching a maximum altitude of 327 kilometers, comfortably within LEO. Vostok 1 was monumental not only for its achievement, but also for its approach. The capsule itself was small, spherical, and lacked the maneuvering capabilities of modern spacecraft. Gagarin could not control the flight manually. Instead, the mission relied entirely on pre-programmed systems. Yet despite the lack of control, the human body held up remarkably well. Gagarin experienced weightlessness, and while the concept of microgravity was entirely new, the flight demonstrated that humans could survive and even function in orbit. The success of Vostok 1 paved the way for more ambitious programs, highlighting both the potential and the limitations of early spaceflight. Shortly after Gagarin's flight, the United States launched its Mercury program aimed at putting an American astronaut into orbit. Between 1961 and 1963, 6 Mercury flights successfully carried astronauts into LEO. Among them, John Glenn's Friendship 7 mission in 1962 marked the first American orbital flight, circling the Earth 3 times in just under 5 hours. The Mercury missions were crucial for several reasons. 1, they confirmed that humans could survive extended periods in microgravity. 2, they tested life support systems, communication protocols, and re-entry procedures. They also provided invaluable data on the psychological effects of isolation and confinement in a tiny capsule moving at orbital velocity. Astronauts reported the thrill of weightlessness. the strangeness of seeing Earth from above, and, in some cases, the disorientation caused by the constant motion and lack of a fixed up or down. These reports would shape every space program that followed, from Gemini to Apollo and beyond. Apollo missions, stepping beyond Leo. While Apollo is most famous for landing humans on the Moon, the early Apollo missions were grounded in Leo first. Apollo 7, for example, launched in October 1968 and orbited Earth for 11 days, testing spacecraft systems and crew performance in extended orbital conditions. These missions refined orbital mechanics, spacecraft operations, and the human experience of life in space. Experiments included evaluating spacecraft thermal control and power systems, testing communication and navigation over long-duration orbital periods, and studying the physical effects of microgravity, including muscle atrophy, fluid shifts, and bone density loss. Leo served as the classroom for astronauts to learn how to live and operate in space before venturing further into the solar system. Without these orbital missions, the moon landings would have been far riskier, and humans would not yet understand the true demands of spaceflight. For decades, Air Leo was dominated by government programs, NASA, Roscosmos, ESA, and other agencies. But the past decade has seen a paradigm shift, as private companies have begun to democratize orbital travel. In May 2020, SpaceX launched Crew Dragon Demo 2, carrying NASA astronauts Doug Hurley and Bob Behnken to the International Space Station, ISS. This mission marked the first time a commercial spacecraft carried humans into orbit. Key details of LEO operations today. Crew Dragon orbits at roughly 408 kilometers within LEO. The spacecraft takes about 8.5 minutes to reach orbit from launch. Astronauts experience weightlessness almost immediately, floating freely within the cabin. The mission highlighted several advances: fully automated docking with the ISS, reducing human workload, reusable rockets, dramatically lowering cost per flight, and enhanced safety systems, including abort capabilities. Since then, SpaceX has continued to launch astronauts and private missions, signaling a new era of commercial access to LEO. Axiom Space, building the first private space station. Another exciting development in LEO is Axiom Space, which plans to build the first commercial space station. Axiom aims to create an orbital platform that supports private astronauts and researchers and provides orbital tourism experiences. It serves as a stepping stone for missions beyond LEO, including lunar operations. These initiatives show that LEO is no longer just a playground for superpower nations. It is becoming accessible to private citizens, researchers, and companies, expanding the human footprint in orbit. Flying in LEO is not just about engineering, it is about the raw human experience. Astronauts face a series of unique challenges, each of which tests the limits of biology and psychology. In LEO, the sensation of weightlessness dominates. The body no longer feels the pull of gravity, and even simple actions like drinking water or moving through the cabin require new techniques. Microgravity affects every system of the human body like muscle atrophy. Without the constant pull of gravity, muscles weaken. Astronauts must exercise at least 2 hours per day to mitigate this effect. And there is bone density loss. Bones lose minerals at a rate of up to 1% per month, a major concern for long-duration flights. There is also fluid shifts. Blood and fluids move toward the head, often causing facial puffiness, nasal congestion, and changes in vision. Despite these challenges, astronauts report a unique psychological benefit: the overview effect. Seeing Earth from orbit, a fragile, glowing sphere suspended in darkness, produces a profound sense of connection and perspective, often described as life-changing. LEO offers some protection from the sun's radiation thanks to the Earth's magnetic field, but astronauts still face higher exposure than on the surface. Prolonged stays in orbit increase the risk of cancer, damage to the central nervous system, and potential cardiovascular problems. Radiation shielding is a key part of spacecraft design, using materials like aluminum, polyethylene, and specialized composites to protect crew members. NASA continually monitors astronaut health to better understand long-term effects. Life in LEO also presents intense psychological pressures. The crew lives in a confined space, isolated from family and the world below, often for months at a time. Challenges include confinement stress and limited privacy. Communication delays with mission control, especially during emergencies, reliance on teamwork and trust in high-stakes situations. Astronauts undergo extensive psychological training before missions to ensure they can cope with these pressures, and space agencies monitor crew mental health closely. The ISS is the pinnacle of human activity in LEO, a permanently inhabited laboratory circling Earth every 90 minutes. Since 2000, the ISS has hosted astronauts from over 19 countries, conducting thousands of experiments in biology, physics, materials, science, and Earth observation. Notable aspects of LEO research aboard the ISS: microgravity experiments that cannot be replicated on Earth, observing Earth's climate, natural disasters, and human activity from orbit. It also includes developing technologies for future long-duration missions to Mars and beyond. LEO serves as the gateway to the cosmos. Low Earth orbit is where human space travel begins and matures. It is here that we test the limits of the human body, experiment with new technologies and spacecraft designs, train astronauts for longer, more distant missions, and begin to imagine life beyond our planet as a permanent possibility, geostationary orbit and beyond. When we talk about space travel, most people picture astronauts floating in the International Space Station, or maybe rockets blasting off to the moon. That's low Earth orbit, the playground where humans first learned how to live above our planet. But just a little higher, about 36,000 kilometers up, lies something even cooler, something far less obvious, but absolutely essential to our lives here on Earth: geostationary orbit. This is the sweet spot where satellites hover over the same spot on Earth all the time, spinning in sync with the planet below. To anyone on the ground, it looks like these satellites are frozen in the sky, silently watching the world, relaying TV signals, tracking hurricanes, guiding GPS satellites, and even supporting internet connections for millions. It's like having invisible guardians above us, orbiting with perfect precision. The idea of geostationary orbit wasn't just pulled out of thin air. Back in 1945, Arthur C. Clarke, the sci-fi writer and space visionary, imagined satellites that could hover over Earth, constantly communicating with the planet below. At the time, it was pure fantasy. Rockets weren't nearly advanced enough, and we didn't know if such a thing could actually work. But today, it's as real as your smartphone or satellite TV, a critical part of our modern world. Geostationary orbit is far beyond the familiar low Earth orbit. While astronauts in LEO orbit the planet every hour and a half, geostationary satellites take 24 hours to complete one orbit, matching Earth's rotation. This means from the ground, they appear completely stationary. You don't see them moving, yet they're hurtling through space at nearly 11,000 kilometers per hour. That's fast enough to circle the globe in just a day, yet somehow they stay fixed over a single spot like magic. Getting there isn't easy. Rockets can't just shoot straight up, they need careful planning. Most satellites start in a lower orbit, a sort of halfway point, before slowly spiraling out to reach geostationary orbit. Every move has to be precise, because a small mistake could send the satellite tumbling into space or straight back into the atmosphere. Once a satellite reaches geostationary orbit, it faces conditions that are extreme, yet invisible. It's completely exposed to the sun and cosmic radiation, unprotected by the thick blanket of our atmosphere that shields us on Earth. Solar panels are constantly bombarded by high-energy particles. Delicate electronics can short-circuit, and even tiny dust particles traveling at thousands of kilometers per hour can chip or damage the surface. Engineers have to design these machines with careful shields and backup systems. Because once a satellite is in orbit, fixing it isn't as simple as sending a technician. Even though humans rarely go this far for now, geostationary orbit is incredibly important for daily life on Earth. Weather satellites here give us early warnings about hurricanes, typhoons, and extreme storms, saving lives every year. Communication satellites make phone calls, TV broadcasts, and internet connections possible across the globe. Navigation satellites help planes, ships, and even you on your smartphone find your way anywhere on the planet. In short, this orbit is like a control room in the sky, quietly doing everything we need without anyone even noticing. But here's the mind-blowing part. Geostationary orbit is still just a drop in the cosmic ocean. It's nearly 10 times closer than the Moon and hundreds of times closer than Mars. While a satellite can circle the Earth every day, humans are limited. We can survive in LEO for months, but beyond that, life support, radiation, and physical limits become serious problems. The gap between geostationary orbit and interplanetary travel isn't just distance. It's a challenge that tests technology, human endurance, and the very limits of what we can achieve. Beyond geostationary orbit lies medium Earth orbit, where GPS satellites circle at around 20,000 kilometers, and then higher Earth orbits for specialized satellites. Each step outward demands more energy, more precision, and more careful planning. Every kilometer farther from Earth is exponentially harder to reach. It's easy to underestimate the scale of space when rockets are so fast and satellites seem so small. We've sent humans to LEO for decades and satellites slightly higher. But when you think about the Moon, Mars, or Jupiter, the numbers get staggering. A robot probe might take months or years to reach these destinations, and humans would face an entirely different set of obstacles. Life support, radiation, psychological pressure. All these make direct human travel to those regions extremely challenging right now. Yet, geostationary orbit is the first stage of all these bigger adventures. It's a place where engineers test new satellites, new propulsion systems, and new communications technologies. Lessons learned here are what make lunar and Martian missions possible. Every rocket that successfully delivers a satellite to geostationary orbit, every maneuver to correct drift, and every experiment in automated systems brings us one step closer to leaving Earth permanently. Private companies like SpaceX, SES, and Intelsat are now launching more satellites than ever, showing that space isn't just for governments anymore. Private citizens, researchers, and corporations are staking claims, experimenting, and pushing the boundaries of what can be done in orbit. And it's not just practical. There's something awe-inspiring about being at geostationary orbit, imagining yourself floating above the Earth, watching entire continents, oceans, and weather systems in real time. To stand or even imagine standing, there is to see the fragility of our planet and the immense possibilities of human ingenuity. While we may not live there, satellites give us a glimpse into a life beyond Earth, a testbed for technology, and a platform for imagining future space stations, hotels, or even colonies high above the planet. In many ways, geostationary orbit is a bridge between what humans can touch and what remains out of reach. It's where technology begins to outpace our bodies, where robots extend our reach far beyond the limits of survival, and where we can operate for years without stepping foot outside. The gap between Earth orbit and interplanetary space is massive, a stark reminder that even our fastest rockets and most advanced technology are still only scratching the surface of the cosmos. But geostationary orbit shows what is possible. Precise engineering, careful planning, and human imagination can extend our influence tens of thousands of kilometers above the Earth. It's also a glimpse into the future. Today, geostationary orbit is home to satellites that power our phones, track hurricanes, and beam television into our living rooms. Tomorrow, it could be home to private space stations, orbital labs, or even vacation destinations for the ultra-rich. Scientists are already testing technologies for long-term habitation, power generation, and station keeping at these heights. The Moon, humanity's first giant leap. For millennia, humans have stared at it, wondering if we could ever touch it, ever set foot on it. And then, in the 1960s, that impossible dream became reality. The moon wasn't just a celestial object anymore. It became a destination, a proving ground, and the first major milestone in humanity's journey beyond Earth. This journey was the Apollo program, NASA's audacious plan to put humans on the moon and bring them back safely. In the midst of the Cold War, the United States and the Soviet Union were locked in a space race, each vying to prove technological superiority and national pride. When Yuri Gagarin orbited Earth in 1961, the Soviets seemed to have the upper hand, but the US responded with determination, committing to President John F. Kennedy's historic promise in 1961. We choose to go to the moon, not because it is easy, but because it is hard. And thus, Apollo was born, a program that would ultimately take humans farther from Earth than anyone had ever gone. The first milestone of Apollo was testing the waters with Earth orbit missions, like Apollo 7 and 8. These missions were about learning to live and operate in space, testing spacecraft systems, and understanding how humans react to prolonged exposure to weightlessness. But it was Apollo 11 that truly captured the imagination of the world. On July 16, 1969, a Saturn V rocket, the most powerful machine ever built at the time, thundered into the sky from Kennedy Space Center, carrying 3 astronauts who would become legends: Neil Armstrong, Buzz Aldrin, and Michael Collins. From Earth to lunar orbit, Apollo 11 traveled 384,000 kilometers, a distance most of us can't even visualize. It took just under 4 days to get there, a blistering speed of 39,000 kilometers per hour during transit. To put that in perspective, they were traveling faster than any human had ever gone before, leaving Earth behind and racing towards a distant, airless world. Every hour brought them farther from home, farther from everything familiar, yet closer to an experience no one had ever lived. Inside the cramped command module, astronauts dealt with constant acceleration during launch, the eerie weightlessness once in space, and the haunting silence that comes from being hundreds of thousands of kilometers from Earth. Every movement had to be precise. Floating in zero gravity wasn't just fun. It required skill to eat, drink, sleep, and operate spacecraft systems. Even the simplest task became a challenge in a cabin the size of a small apartment. Yet the crew remained focused, their training and nerves of steel guiding them through one of the most dangerous journeys ever attempted. The Saturn V rocket had 3 stages, each one a fire and brimstone spectacle, designed to peel away sequentially and keep the astronauts on their trajectory. One failure in any stage could mean instant disaster. The world watched nervously as Apollo 11 climbed into the sky, engines roaring, fire and smoke trailing like the tail of a comet. And then, after the 3rd stage burned out, the astronauts found themselves in a state that no human had ever experienced: the quiet, weightless void of space, Earth shrinking behind them as a pale blue dot in the distance. When Apollo 11 entered lunar orbit, the thrill escalated. The command module, piloted by Michael Collins, circled the moon, while Armstrong and Aldrin prepared to descend in the lunar module Eagle. The modules separated, and suddenly they were alone in a small spacecraft, heading to a surface that no human had ever walked on. The descent was terrifying, fraught with obstacles, radar alarms, computer glitches, and the knowledge that one wrong maneuver could send them crashing into the lunar surface. Yet, despite the tension, the astronauts executed their landing perfectly, touching down in the Sea of Tranquility on July 20, 1969. The moon was otherworldly. The grey dust, fine as flour, coated every surface. Craters and hills stretched endlessly, casting deep shadows across a stark landscape illuminated by the sun. Armstrong's first step onto the lunar surface was broadcast live, millions of people around the world holding their breath as he spoke the words that would echo through history. That's one small step for man, one giant leap for mankind. And in that moment, humanity realized that we could leave our home planet, survive in space, and walk on another world. The gravity was just 1/6 of Earth's, making every step feel exaggerated, almost bouncing. Walking, bending, lifting tools all required adjustment. Even simple movements became complex tasks. Buzz Aldrin described the feeling as like walking on a trampoline, while Armstrong marveled at the surreal stillness. Despite the desolation, the astronauts conducted experiments, collected samples, and planted the American flag, marking a moment both symbolic and practical. Every rock they picked, every measurement they took, provided invaluable scientific data about the Moon's composition, formation, and history. But life on the Moon was far from leisurely. The astronauts faced extreme temperatures, deadly radiation, and the constant awareness that a single mistake could be fatal. They wore heavy pressurized suits to survive, their mobility restricted, their every action deliberate. Sleeping, eating, and even moving around the lunar module required careful planning. Yet, despite the danger and discomfort, the astronauts reveled in the moment, the thrill of being the first humans to touch a world beyond Earth. The return journey was just as critical. Leaving the lunar surface required launching from a spacecraft perched precariously on the Moon, docking with the orbiting command module, and then beginning the long trip back to Earth. The return trajectory required precise calculations. A misalignment could send the spacecraft into deep space or doom it to crash. Once again, the Saturn V rocket's smaller engines were replaced by the lunar module's ascent engine, a tiny but powerful piece of engineering that had to perform flawlessly. And it did. Re-entry into Earth's atmosphere was an entirely different ordeal. Traveling at over 39,000 kilometers per hour, the command module had to endure immense friction, heat, and pressure. Temperatures outside soared to thousands of degrees Celsius, and the spacecraft relied on a heat shield to survive. Inside, astronauts felt intense vibrations and forces that pressed them into their seats, a physical reminder of just how fast and far they were traveling. And then, finally, the capsule parachuted into the ocean, splashing down safely, completing a journey of nearly 770,000 kilometers round trip, a feat that had never been attempted before and may never be repeated in exactly the same way. Apollo missions didn't stop with 11. They continued through Apollo 17, refining the experience of living and working on the Moon, testing new landing techniques, exploring new areas, and learning more about our closest celestial neighbor. Apollo 12, 14, 15, 16, and 17 each pushed boundaries further. Longer stays, more sophisticated experiments, roving vehicles to explore greater distances, and increasing scientific data that would inform our understanding of planetary geology and space travel. Each mission improved our understanding of living in low gravity, handling extreme temperatures, and conducting meaningful work far from Earth. The Apollo program also showed the world how far humans could go in a lifetime. The Moon is 384,000 kilometers away, a distance that dwarfs the daily experiences of astronauts in low Earth orbit or even geostationary orbit. The speed of travel, the precision required, the danger involved, all highlighted the incredible achievement of placing humans on another world and returning them safely. It set the stage for every future mission, proving that with courage, planning, and determination, humans could survive beyond Earth and work effectively in space. Yet perhaps the most important part of Apollo wasn't the rockets, computers, or technical achievements. It was the human experience. Floating in the command module, landing on a desolate world, conducting experiments in alien gravity, and returning home safely transformed the astronauts forever. They described awe, fear, exhilaration, and the surreal realization of being so far from everything familiar. Millions of people around the world shared that experience in a small way, watching television broadcasts that captured the Moon's barren beauty and the astronauts' careful steps. Apollo turned a distant rock in the sky into a real place, tangible, reachable, and filled with human stories. Even today, Apollo shows that humans can leave our home planet, travel hundreds of thousands of kilometers, survive in hostile environments, and conduct meaningful work on another world. It's the first major milestone, that proves we can go farther than we've ever gone, and it inspires every mission that follows, from robotic explorers of Mars to plans for lunar bases and beyond. Returning to the Moon Artemis, Chang'e, and the future of lunar travel. When humans last set foot on the Moon, it was 1972, Apollo 17. Since then, nearly 50 years passed with no boots touching the lunar surface, and the Moon became a silent sentinel in the night sky, watched by telescopes, orbiters, and a handful of robotic probes. But in the last decade, everything changed. NASA's Artemis program promises to send humans back to the Moon, while China's Chang'e missions are systematically mapping, landing, and even returning samples. Meanwhile, private companies like SpaceX and Blue Origin are plotting the first lunar tourist flights, turning what was once impossible into an eventual reality. The modern Moon is no longer just a celestial object, it's a destination, and the race to get there is heating up. Artemis, NASA's audacious plan, aims to land astronauts near the lunar South Pole, an area that has never been explored by humans. Unlike Apollo, Artemis is designed as a sustainable multi-stage campaign. The launch system, the Space Launch System, SLS, is a towering beast, capable of lifting 95 tons into orbit, more than double the payload of the Saturn V rockets used in the 1960s. When SLS ignites, its engines unleash a raw, ear-shattering fury, propelling astronauts at roughly 39,000 kilometers per hour, the speed necessary to escape Earth's gravity and reach the Moon in roughly 4 days. But the speed is only part of the story. Artemis missions are carefully choreographed, using Earth-Moon transfer orbits, a looping trajectory that allows astronauts to conserve fuel while maximizing payload efficiency. Fuel isn't just a number, every kilogram matters. The modules carrying astronauts, supplies, and lunar landers must be balanced with exact precision, or the entire mission risks missing the Moon entirely. China's Chang'e program takes a different approach, gradually pushing human reach via robotic exploration. Chang'e 4, for instance, landed on the Moon's far side in 2019, a historic first. These missions are focused on mapping the lunar surface, testing autonomous landers, and even retrieving lunar soil for study on Earth. Chang'e 5 succeeded in returning samples in 2020, a feat that required precise orbital mechanics, propulsion timing, and fuel efficiency to make the round trip. These robotic missions illustrate the challenges any human mission would face. Propulsion must be meticulously planned, travel speeds must balance acceleration and fuel load, and every trajectory must account for the Moon's gravitational quirks and the Earth-Moon orbital dance. The physics of the journey are as brutal as they are fascinating. To leave Earth's orbit and reach the Moon, rockets must first overcome escape velocity, roughly 40,270 kilometers per hour. Achieving this requires enormous amounts of fuel, finely tuned engines, and exact timing. SLS, Falcon Heavy, or even Starship must carry not just the crew, but supplies for survival: life support, oxygen, water, food, radiation shielding, and propulsion for lunar landing and ascent. The timing of burns, the use of gravitational assists, and the choice of orbital insertion points all determine whether a spacecraft arrives at the Moon on schedule or drifts into the void. Time in transit is deceptively short in cosmic terms. 4 days may sound manageable, but inside a cramped spacecraft traveling at 39,000 kilometers per hour, every second is high stakes. There's no room for error. A miscalculation of even a few seconds in the burn sequence could throw the mission off by thousands of kilometers, forcing either a dangerous course correction or an aborted landing. The astronauts have to execute every maneuver flawlessly, relying on both onboard computers and ground support thousands of kilometers away, coordinating across a time delay that, though brief, adds tension. Once the lunar orbit is achieved, Artemis astronauts will transfer to a lander designed for a precise descent. The lander's engines must slow the spacecraft dramatically from tens of thousands of kilometers per hour in translunar speed to a crawl over the surface, touching down at mere 1.6 kilometers per second relative to the Moon. Fuel here is extremely limited. Every kilogram burned reduces the available margin for error. Unlike Apollo, Artemis aims to support longer stays, which means planning for repeated ascents, perhaps reusable landers, and supply modules pre-positioned for extended exploration. China's approach also demonstrates the logistics of precision lunar travel. Chang'e 5, for instance, launched a lander, collected samples, and then ascended to lunar orbit for rendezvous with an orbiter, a process requiring perfect timing and navigation. The ascent stage had to match speed and trajectory with the orbiting module, all while conserving fuel and avoiding the gravitational traps of lunar mass concentrations, known as mascons, which can subtly alter trajectories, miss even a minor correction, and the entire mission could fail. For human missions, this means planning for redundancy, backup engines, and life support contingencies, making lunar travel a careful balance between speed, efficiency, and safety. Then there's the emerging world of lunar tourism. SpaceX is actively developing plans for Starship lunar missions, aiming to carry private passengers on circumlunar flights. Unlike Artemis, which lands astronauts on the Moon's surface, these missions may loop around the Moon and return to Earth, providing the first taste of civilian deep space travel. A trip like this is less than a week, but the experience is intense. A full view of the Moon's far side, the blackness of space, and the curvature of Earth hanging like a marble in the void. Blue Origin has also indicated lunar tourism ambitions, with landers capable of short hops and potential lunar flybys, though their timelines are more tentative. These ventures bring unique logistical challenges. Private spacecraft must carry humans safely, account for radiation exposure beyond Earth's magnetic field, and execute high-speed trajectories with no room for error, all while providing the comfort and accessibility expected by non-professional astronauts. Realistically, how far could humans stay or return from the Moon today? Short missions of a few days are feasible, especially with robust life support and propulsion systems, like those Artemis is building. Beyond that, the limitations multiply quickly. Radiation is relentless. Without the protection of Earth's magnetic field, astronauts face cosmic rays and solar particle events, requiring thick shielding or rapid retreat protocols. Oxygen, water, and food must be precisely calculated. Every additional day in lunar orbit or on the surface increases mass requirements exponentially, and with every kilogram comes fuel, which in turn adds more mass, a cascading challenge in space logistics. Landing further afield, like the lunar South Pole, compounds these issues with rough terrain, temperature extremes, and communication delays. While short stays of a week or two are technically feasible, longer-term habitation, weeks, months, or years, remains limited by supplies, radiation exposure, and propulsion constraints for a safe return. Even the return journey is a logistical ballet. Leaving lunar orbit requires the lander to accelerate from the Moon's escape velocity, roughly 2.4 kilometers per second, and rendezvous with orbiting modules. Any delay or miscalculation can leave astronauts stranded or force them to use contingency fuel, reducing flexibility. The spacecraft then must execute a precise translanar injection burn to intersect Earth orbit at the correct angle. Too steep and the module burns up, too shallow and it skips off the atmosphere into space. Re-entry is the same high-speed ordeal Apollo crews endured, traveling at over 39,000 kilometers per hour, facing immense heat and pressure, relying on heat shields and parachutes to ensure survival. These are calculations every mission must master, whether it's government-funded or private tourism. Fuel requirements alone are staggering. Reaching the Moon, landing, ascending back, and returning safely to Earth demands thousands of tons of fuel, carefully distributed across stages. Modern rockets like SLS or Starship are designed for efficiency, but the energy required to push humans and cargo out of Earth's gravity well and back is immense. SpaceX Starship, with fully reusable stages, attempts to reduce costs and increase flight frequency, but every launch is still a complex orchestration of mass, speed, and trajectory. For a lunar tourist, this translates to strict limitations on how long they can stay, how much cargo can be carried, and the exact path the spacecraft must follow. The Artemis program is also experimenting with pre-positioned cargo and refueling stations in lunar orbit, which could extend mission durations and reduce the fuel burden on landers. Chang'e missions demonstrate the potential for automated refueling, sample return, and precise orbital insertion, lessons that could one day enable human astronauts to stay longer on the Moon, though not indefinitely. Even so, for now, any human presence is necessarily short-term, bounded by fuel, life support, and radiation. There's no permanent lunar colony yet, no fully self-sustaining lunar base, and every mission requires a meticulously planned return trajectory. Mars, humanity's next frontier. Looking up at the night sky, Mars glows like a tiny reddish ember, a faint pinprick of fire that has fascinated humans for centuries. We've stared at it through telescopes, imagined our names on its dusty plains, and dreamed of what it would feel like to leave Earth behind and touch another planet. But this is no fantasy. Unlike the Moon, which sits a few 100,000 kilometers away, Mars is millions of kilometers distant, a journey that would push human space travel to its absolute limits. It is, for now, the most realistic deep space goal a human could achieve in a lifetime. A destination that is both terrifying and mesmerizing, and the next giant leap in exploration. The distance to Mars is not constant. Depending on where Earth and Mars are in their respective orbits, it can be anywhere from 55 million kilometers at closest approach to 400 million kilometers when the planets are on opposite sides of the Sun. That's the kind of scale that makes you feel instantly small. Unlike lunar missions, which last a matter of days, a Mars trip with current chemical rockets takes roughly 6 to 9 months, one way, meaning astronauts are in deep space for nearly a year just to reach the planet, and then another 6 to 9 months to return home. And that's if everything goes perfectly. Every day, every maneuver, every calculation becomes a high-stakes problem with no room for error. Today, a handful of organizations are seriously plotting how to make this possible. NASA's Mars plans aim for carefully staged missions, with robotic precursors laying the groundwork for human landings, testing life support systems, mapping potential habitats, and identifying resources that could be used once humans arrive. SpaceX, with its Starship program, has set the boldest goals, sending humans on relatively direct journeys to Mars, carrying dozens of passengers in a single flight, and potentially establishing the first permanent bases. International agencies, including ESA, Roscosmos, and CNSA, are also exploring joint missions, often focusing on robotic precursors, but with the long-term vision of human exploration. Each plan involves millions of calculations, years of training, and hardware pushed to the absolute limits of engineering. The journey to Mars starts with launch. Rockets must escape Earth's gravity, accelerating crews to around 39,000 kilometers per hour, the same escape velocity used for moon missions, but sustained over a much longer trajectory. Unlike a lunar flight, which takes just 4 days, astronauts bound for Mars are in free space for months. During this time, the spacecraft must provide everything humans need: oxygen, water, food, waste management, radiation shielding, and a pressurized environment where the crew can sleep, eat, and work. Space isn't just hostile, it's completely indifferent to human life. A single failure in life support could be fatal, and redundancy is mandatory. Multiple backups, redundant power systems, and automated emergency procedures all work together to keep humans alive on this extended voyage. Chemical rockets, the workhorse technology of today, are fast enough to get humans to Mars, but only barely. The journey is long and unforgiving. If astronauts need to abort and return to Earth mid-mission, they face complex orbital mechanics and limited fuel margins. Every kilogram added to the spacecraft for shielding or supplies adds fuel requirements, which in turn increases mass, requiring even more fuel, creating a delicate balancing act that engineers describe as mass budgeting at its absolute extreme. The longer humans stay in space, the more critical this balance becomes. SpaceX Starship, with its fully reusable design and enormous payload capacity, aims to solve some of this problem by carrying larger crews and more supplies. But even then, the journey is a months-long endurance test, not just of technology, but of human bodies and minds. Radiation is one of the biggest invisible threats on the way to Mars. Unlike Earth, which is protected by its magnetic field and thick atmosphere, the journey through interplanetary space exposes astronauts to cosmic rays and solar particle events. These high-energy particles can damage cells, increase cancer risk, and interfere with neurological functions. Spacecraft rely on shielding, sometimes water or fuel walls arranged around the crew compartment to reduce exposure. But nothing currently available can block all radiation without massively increasing spacecraft mass. Engineers are exploring new materials, magnetic shielding concepts, and even deep space storm shelters inside the spacecraft, where astronauts could take refuge during solar flares, but radiation remains a constant invisible danger throughout the voyage. Microgravity adds another layer of complexity. Even 6 to 9 months in near weightless conditions can wreak havoc on the human body. Bones lose density, muscles atrophy. The cardiovascular system adjusts to low gravity in ways that make returning to Earth physically demanding. NASA and other agencies have studied this extensively on the ISS, where astronauts experience these effects over 6-month stints, but Mars adds an unprecedented layer of duration. Some proposed spacecraft designs incorporate artificial gravity concepts, rotating sections that could generate centrifugal force to mimic gravity, but these are still in experimental stages. Without careful countermeasures, astronauts risk returning to Earth weakened, frail, and more susceptible to injury. The psychological challenge is just as intense. Months of isolation, confined quarters, and reliance on a tiny crew can amplify stress, anxiety, and interpersonal tension. Communication delays with Earth, ranging from 4 to 24 minutes one way depending on planetary positions, mean astronauts cannot get immediate help or advice. They are alone in a literal void, relying on training, discipline, and each other. Sleep cycles, recreation, and carefully managed routines are critical, and even then, astronauts face monotony and sensory deprivation, unlike anything on Earth. Long-duration missions require not just physical endurance, but extraordinary mental resilience, the ability to stay calm and functional when every decision carries life or death consequences. Once at Mars, the challenge shifts from surviving the journey to surviving the planet itself. Landing on Mars is far more complicated than landing on the Moon. Mars has an atmosphere, thin but enough to create friction, and gravity that is roughly 38% of Earth's. A lander must decelerate from orbital speeds, roughly 5,000 kilometers per hour, through this thin atmosphere without relying entirely on parachutes or retrothrusters. Engineers call it the 7 minutes of terror, the final descent that must perfectly balance aerodynamics, engine thrust, and trajectory to prevent catastrophic failure. The rover landings we've seen from NASA's robotic missions demonstrate how difficult it is even for automated systems. Humans add weight, complexity, and a requirement for survivable landing conditions. Once on the Martian surface, everything becomes logistically demanding. Life support must recycle oxygen, manage carbon dioxide, and supply clean water. Temperatures swing from -125 degrees Celsius at night to 20 degrees Celsius at the equator during the day, meaning habitats must be insulated, pressurized, and capable of handling extreme temperature variations. Dust storms can last for weeks, coating solar panels, reducing power generation, and creating hazards for mobility. Even mobility itself is challenging. Astronauts must move carefully in bulky suits, limiting exploration speed and increasing fatigue. Supplies must be carefully rationed or pre-positioned by robotic missions, because resupply from Earth is not an option without months-long wait times. SpaceX's Starship offers a unique approach to this problem. With the potential to carry dozens of passengers, Starship could enable larger crews, more supplies, and longer stays on Mars. Refueling in orbit and pre-positioning fuel depots could extend mission durations and allow repeated trips, gradually building a semi-permanent human presence. NASA's more cautious approach focuses on smaller crews, shorter missions, and extensive testing of life support systems and habitats, laying the groundwork for sustainable exploration over decades. Both approaches highlight the delicate balance of speed, fuel, crew size, and resource management required for realistic Mars missions. Even with the most advanced technology, humans cannot stay on Mars indefinitely yet. Life support must handle months of continuous operation without resupply. Radiation shielding must remain intact. Habitats must maintain pressure, temperature, and air quality, and every system must have redundant backups. Long-term habitation, years at a time, is theoretically possible but remains beyond current capabilities. For now, realistic human missions focus on flyby missions, orbital missions, or stays measured in weeks or months, with careful contingencies for every phase of the journey. Travel logistics continue to be one of the most limiting factors. The round-trip distance varies enormously. During optimal alignment, astronauts travel about 110 million kilometers round-trip. But when orbits are less favorable, that distance balloons to 800 million kilometers, making mission timing, propulsion, and fuel efficiency absolutely critical. Orbital mechanics dictate launch windows, limiting opportunities for departure to once every 26 months when Earth and Mars align favorably. Missing the window can delay a mission by more than 2 years, meaning astronauts must endure extended stays in transit or wait on Mars until the next opportunity for return. Beyond Mars, testing the limits of human reach in our solar system. The farther you go from Earth, the more the familiar fades. Mars glows faintly red in the sky, but beyond it lie the giant planets, swirling storms, and frozen worlds that seem almost alien. Jupiter, Saturn, Uranus, Neptune, these are not just distant dots in the sky. They are enormous challenges of distance, speed, and survival, the ultimate test of how far humans could travel with today's technology. Jupiter, the largest planet in the solar system, sits roughly 628 million kilometers from Earth on average, though that distance varies depending on where the planets are in their orbits. Saturn, famous for its rings, is about 1.2 billion kilometers away, Uranus around 2.6 billion, and Neptune a staggering 4.3 billion kilometers distant. The scale is almost unimaginable. To put this into perspective, the Moon, humanity's first target, is less than 0.4 million kilometers away. Mars, our next frontier, is 55 to 400 million kilometers. Now imagine multiplying that distance several times and asking, could a human ever get there in a lifetime? With current chemical rockets, the answer is sobering. Apollo rockets reached the Moon in 4 days, Mars in roughly 6 to 9 months. Jupiter, with its average distance, would take about 6 years one way using chemical propulsion at the speeds we can achieve today. Saturn, at least 12 years. Uranus and Neptune, decades. Even if you packed a human lifetime with all your waking hours in space, traveling to the outer planets with today's technology becomes almost impossible. That's why no human has ever ventured beyond Mars. Every mission beyond is robotic, designed to survive where humans cannot yet go. We've sent machines to these distant worlds, and they are our eyes and ears. Voyager 1 and 2, launched in 1977, remain some of the most remarkable achievements in space exploration. Voyager 2 flew past Jupiter, Saturn, Uranus, and Neptune, sending back detailed images and measurements. It took Voyager 2 over 12 years just to reach Neptune, and even then, it wasn't slowing down. It continued on a trajectory out of the solar system. Voyager 1 is now more than 23 billion kilometers from Earth, traveling in interstellar space. These missions show the gap between robotic and human reach. A probe can survive decades in harsh environments without food, water, or radiation shielding. A human cannot. New Horizons, which famously flew past Pluto in 2015, traveled at 16 kilometers per second, roughly 58,000 kilometers per hour, and reached Pluto in about 9.5 years. That speed is blistering, faster than any human spacecraft has ever gone. yet it barely scratches the distances involved in interplanetary travel beyond Mars. The energy required to push a human crew to these speeds, while also carrying life support, food, water, radiation shielding, and fuel for maneuvering, makes current chemical propulsion completely impractical for human missions to Jupiter or beyond. Juno, NASA's mission orbiting Jupiter since 2016, demonstrates how precision and energy efficiency become critical in the outer solar system. Juno carries enough fuel to adjust its orbit, but relies primarily on gravity assists and precise trajectory planning. It orbits a planet with a gravity field 2.5 times stronger than Earth's, enduring radiation belts so intense that its electronics must be specially shielded. Sending humans into that environment would be orders of magnitude more complex, not just survival in vacuum, but withstanding massive radiation doses that would otherwise be fatal without thick shielding. Shielding that adds tremendous mass and thus more fuel, creating a cycle of limits that rockets cannot currently overcome. Even if we could launch humans, the time in transit is staggering. Let's take Jupiter as an example. A chemical rocket, similar to current Mars missions but scaled for distance, could take 5 to 6 years one way. Life support for that long is a huge challenge. Water recycling systems must operate flawlessly for years. Food must either be stored for the entire journey or grown in space, requiring hydroponics or bioregenerative systems that are still experimental. Oxygen must be produced or recycled efficiently, and carbon dioxide scrubbers must never fail. Medical emergencies, mental health crises, or equipment malfunctions in deep space would be catastrophic because immediate help from Earth is impossible. Saturn, at 1.2 billion kilometers away, pushes these limits even further. A chemical rocket would take roughly 12 years to arrive, and that's under ideal conditions. Uranus and Neptune, over 2.5 and 4 billion kilometers away, would require decades of travel, far longer than a typical human lifetime. Even if astronauts were launched at a young age, they would arrive in old age, or not at all, making the idea of human exploration of these worlds with current propulsion technology unrealistic. The distances impose constraints on fuel, energy, and life support that technology simply cannot meet today. That's why, for the outer planets, robotic missions dominate. They can carry instruments, cameras, sensors, and even small landers, all without the need for food, oxygen, or radiation shielding for living beings. Voyager 2's flybys of Jupiter, Saturn, Uranus, and Neptune gave us knowledge that humans could never have gathered directly. Juno's close orbit around Jupiter has mapped magnetic fields and atmospheric storms in incredible detail, something impossible for a crewed spacecraft to endure. New Horizons gave us the first close-up images of Pluto and Charon, proving that we can explore the edges of the solar system with robots long before humans can set foot there. But humans have never stopped dreaming. There's news almost every year of proposed missions that push the envelope. NASA and international space agencies are exploring nuclear propulsion, which could reduce travel times dramatically. Nuclear thermal rockets or nuclear electric propulsion could, in theory, cut the trip to Jupiter from 6 years to a couple of years, and to Saturn from 12 years to maybe 3 or 4. These technologies remain experimental, but represent humanity's best hope for extending our reach while keeping astronauts alive. Concepts like Project Orion in the 1960s imagined nuclear pulse propulsion, detonating small nuclear charges behind a spacecraft to propel it forward. Today, engineers are looking at safer, controlled nuclear fission or even fusion-powered engines. If successful, these could finally make human travel to the outer planets feasible within a single human lifetime. Energy requirements are enormous. Pushing a spacecraft with a multi-ton crew module, life support, and supplies to speeds sufficient to cross billions of kilometers in years requires energy far beyond chemical rockets. Nuclear propulsion could provide continuous acceleration over months, reducing travel time and mitigating some life support challenges. But engineering a reactor that can operate safely in space, handle vibrations, and not poison the crew is a monumental challenge. It's a frontier of physics, engineering, and human endurance all at once. Fuel limitations are another hard wall. Chemical rockets require enormous mass ratios. Most of the spacecraft's initial mass is fuel, just to escape Earth, perform mid-course corrections, and decelerate at the destination. Every kilogram of shielding, water, or food adds fuel requirements exponentially. That's why all robotic missions to Jupiter, Saturn, Uranus, and Neptune rely on gravity assists, slingshot maneuvers using planets like Venus, Earth, or Jupiter itself to gain speed without burning extra fuel. Humans with life support systems and habitats can't rely on extreme gravity assists in the same way, making propulsion a major bottleneck for deep space crewed travel. Radiation remains the invisible killer. Once beyond Mars, the Sun's magnetic protection weakens dramatically, and cosmic rays bombard spacecraft relentlessly. Jupiter's radiation belts are hundreds of times stronger than anything near Earth, and Saturn, Uranus, and Neptune all exist in environments where high-energy particles are unavoidable. Shielding against these threats increases mass, which increases fuel requirements, which increases mission complexity, an almost impossible loop to break with current technology. Mental health is another challenge that grows with distance. For Mars, Earth is far, but still visible in the sky. For Jupiter or Saturn, Earth becomes a faint point of light. Communication is delayed by tens of minutes, and isolation becomes acute. Crews could not rely on instant support or rescue. Months of confinement, interstellar monotony, and the knowledge of being millions of kilometers from help would test even the most resilient astronauts. Psychology is as critical as propulsion in deep space missions. Yet it is far harder to solve, with distance increasing by orders of magnitude. Despite all these limits, humanity continues planning. NASA's conceptual studies for crewed Jupiter flybys involve multi-decade missions, using nuclear propulsion or staged habitats to keep humans alive for years. Private companies inspired by SpaceX's Starship imagine long-duration missions to Jupiter's moons like Europa, although these remain theoretical. Robotic precursors continue to explore every corner. Europa Clipper will map Jupiter's icy moon, Europa. Dragonfly will visit Titan, and future missions may carry landers or sample return systems to Ganymede or Enceladus. These missions provide a blueprint for what human explorers might do decades or centuries from now if propulsion, shielding, and life support catch up. Life support scaling is one of the most unforgiving limits. A Mars mission requires months-long recycling of air and water. Beyond Jupiter, travel times extend to years. Supplies cannot simply be carried. Spacecraft must generate or recycle everything, with redundancy for years without resupply. Energy for heating, pressurization, and radiation shielding must come from reactors or enormous solar arrays, which themselves add mass and complexity. Fuel limitations and propulsion efficiency are inextricably tied to these calculations. The farther out you go, the more extreme the requirements become, until with chemical rockets, humans simply cannot reach the outer planets in a single lifetime. Robotic versus human missions are a constant comparison. Robots like Voyager, Juno, and New Horizons can travel decades, operate in lethal radiation, and survive deep space temperatures. Humans require life support, shielding, and continuous power. Every additional year multiplies the logistical burden. This is why Jupiter, Saturn, Uranus, and Neptune remain the realm of robotic explorers, and why humans must wait for breakthrough technologies like nuclear propulsion, artificial gravity, and self-sustaining habitats to ever set foot there. Even travel speed is a hard constraint. With chemical rockets, humans cannot exceed tens of kilometers per second without carrying unimaginable amounts of fuel. Voyager 1 left Earth at roughly 17 kilometers per second, already faster than any crewed vehicle, yet it took decades to cross the solar system. To carry humans at those speeds would require massive propulsion systems, shielding, and onboard energy, all of which push current engineering to the brink. Travel beyond Mars is a test not just of endurance, but of energy, logistics, and physics itself. Future mission proposals are bold. Nuclear thermal rockets, fusion concepts, and high-efficiency ion drives could cut travel times by factors of 2 or more. JAXA, NASA, and private companies continue researching propulsion technologies that might one day allow humans to leave Mars' orbit and venture to the gas giants in years instead of decades. Even then, crews would face months in transit, extreme radiation, psychological challenges, and massive engineering complexity. The limits of human reach in our solar system are concrete constraints imposed by physics, mass, and human biology. The outer limits humanity and the Kuiper Belt. Beyond Neptune lies a vast frozen wilderness that stretches to the very edges of the Sun's gravitational influence. The Kuiper Belt, a sprawling ring of icy worlds, dwarf planets, and countless rocky fragments, represents the outer limits of our solar system. Unlike the Moon, Mars, or even Jupiter, these objects are hundreds of millions to billions of kilometers from Earth, a scale that dwarfs anything humans have yet attempted to travel. Pluto, the most famous Kuiper Belt object, sits roughly 4.6 billion kilometers away, a staggering distance that makes human travel there seem almost unimaginable with today's technology. Beyond Pluto, Eris lurks in the darkness, around 10 billion kilometers from the Sun, and Haumea orbits in a highly elongated path, tens of billions of kilometers from Earth at certain points. Reaching these objects is not a matter of months or years. It is a question of decades, propulsion limits, and life support systems that currently do not exist for such journeys. Robotic exploration has been our only window into the Kuiper Belt so far. New Horizons, launched in 2006, represents the pinnacle of long-range planetary missions. It sped past Jupiter for a gravity assist, gaining speed that would eventually carry it across billions of kilometers. In July 2015, it became the first spacecraft to visit Pluto, revealing mountains of ice, vast plains, and a surprisingly active surface. The speed of the mission is almost incomprehensible. Traveling at over 16 kilometers per second, New Horizons crossed the distance to Pluto in just over 9 years, a journey that would take humans multiple lifetimes with current chemical rockets. Its success illustrates the enormous challenge of sending humans to Kuiper Belt objects. Even the fastest robotic mission takes nearly a decade, and that's without needing life support, food, water, radiation shielding, or fuel for landing and return. Pluto itself is a world of extremes. It has a surface temperature around -229 degrees Celsius, with a tenuous atmosphere that collapses and freezes seasonally. Gravity is a mere 6% of Earth's, meaning any human would have to adapt to movement and balance in near-zero conditions. Landing on Pluto presents its own problems. The thin atmosphere makes parachutes almost useless, requiring powered descent with retro rockets, and the extreme cold affects machinery, electronics, and potential habitat systems. The energy needed to land humans there, survive for even a short period, and return safely is orders of magnitude beyond what chemical rockets can deliver. Beyond Pluto, Eris pushes the limits even further. Discovered in 2005, Eris is slightly smaller than Pluto, but more massive, orbiting the Sun in a path that takes it up to 14.6 billion kilometers away at aphelion. A robotic mission to Eris would take decades, and a human mission is essentially impossible without breakthrough propulsion. Nuclear thermal rockets, nuclear electric drives, or even speculative fusion propulsion are the only technologies that could reduce travel time to something conceivable for a human lifetime. Even then, we are talking years in transit, requiring massive life support, supplies, radiation shielding, and psychological resilience. Haumea, with its elongated orbit and rapid rotation, presents a different challenge. Its distance varies dramatically depending on where it is in its orbit, from roughly 6 billion kilometers to nearly 12 billion kilometers. Haumea's rapid spin means a human landing would have to account for centrifugal forces affecting both the surface and any deployed modules. Its low gravity, less than 5% of Earth's, would complicate mobility, habitat stability, and fuel use for landers. Even robotic missions need precise navigation, timing, and energy planning to reach Haumea safely. Travel speed is the defining limitation for human reach in the Kuiper Belt. With chemical rockets, even a direct trajectory to Pluto would take decades, during which astronauts would need fully functional life support for the entire period. Water recycling, oxygen generation, food storage, and waste management must operate continuously without failure for multiple decades, a level of reliability that does not yet exist for human spaceflight. Any malfunction could be fatal, and there is no rescue option. Radiation shielding is another huge challenge. In the outer solar system, the Sun's protective magnetic field weakens, and cosmic rays bombard spacecraft constantly. Shielding thick enough to protect humans adds mass, which increases fuel requirements exponentially, which in turn further complicates propulsion. Every kilogram counts, and the farther the target, the more severe the constraints become. Even with advanced propulsion concepts, human missions to Kuiper Belt objects are limited by fuel, speed, and life support. Nuclear thermal rockets could, in theory, provide continuous acceleration over months, cutting decades-long journeys to perhaps a few years. Nuclear electric propulsion, using ion drives powered by a reactor, could provide high-efficiency thrust over long durations. But this requires extremely advanced power management, radiation protection, and highly reliable systems capable of operating for years without repair. Fusion propulsion, while still purely theoretical in practical terms, might allow even faster travel, but it is decades away from practical implementation. Without these breakthroughs, human missions remain impossible within a single lifetime. Communication delays also impose limits. At Pluto's distance, signals from Earth take roughly 4.5 hours one way. For Eris, this extends to over 9 hours, meaning astronauts could not rely on immediate support from mission control. Every maneuver, every correction, every life-critical decision would have to be autonomous or pre-planned, increasing both the risk and complexity of missions. For robotic missions, this is manageable, as computers can execute commands automatically. For humans, this isolation magnifies stress and requires psychological preparation on an unprecedented scale. Life support scaling is particularly unforgiving. On Mars, months-long missions already push the limits of oxygen, water, and food recycling. In the Kuiper Belt, missions stretch to years or decades. Every additional kilogram of food, water, or shielding increases the fuel requirement dramatically. Generating energy becomes more difficult as solar intensity drops to a fraction of what it is near Earth. At Pluto, sunlight is about 1/1600th as strong as at Earth orbit, meaning solar panels are largely useless without enormous surface area, and nuclear power becomes the only viable option. The spacecraft must carry fuel for propulsion, heat, electricity, and redundancy for decades, all while maintaining a livable environment for humans, an engineering problem of staggering scale. Robotic missions demonstrate how far we can go with current technology. New Horizons' flyby of Pluto was carefully timed, relying on a gravity assist from Jupiter to reach its target in under a decade. It carried enough fuel to make minor course corrections, but landing or orbiting Pluto would require orders of magnitude more fuel, especially for a human mission. The spacecraft's instruments were designed for longevity in extreme cold, radiation, and distance, showing the engineering precision needed for survival. For humans, replicating this success multiplies the complexity hundreds of times. Future mission proposals continue to push boundaries. NASA, ESA, and private companies have considered orbiters or flyby missions to Kuiper Belt objects. Concepts include multi-decade trajectories using nuclear propulsion, pre-positioned habitats or fuel depots, and autonomous robotics to scout locations before humans arrive. Some proposals envision crude flybys of Pluto or other large KBOs, where humans would pass within tens of thousands of kilometers, conduct observations and return, similar to a long-range version of Apollo lunar flybys. Even flybys would take years of travel in deep space, requiring life support and shielding far beyond anything ever built for humans. Energy requirements are extreme. Chemical rockets simply cannot provide the sustained thrust needed to traverse billions of kilometers within a human lifetime. Every kilogram of mass, from the habitat to shielding to food, compounds the energy problem. Ion drives or nuclear propulsion are the only conceivable alternatives, but they require decades of technological development and testing to reach the reliability needed for crewed missions. Even with breakthroughs, distances remain daunting. A journey to Pluto, Eris, or Haumea is measured not in days or months, but in years and decades. Radiation and microgravity compound these challenges. Extended travel times mean prolonged exposure to cosmic rays and solar particle events. Unlike Earth or Mars, there is no significant gravity to help maintain human health. Microgravity over years leads to severe muscle atrophy, bone density loss, and cardiovascular changes. Psychological isolation becomes extreme. Every system must work perfectly for decades, with no repair options, making the technical and human challenges of Kuiper Belt travel unlike anything humanity has ever attempted. The Kuiper Belt also presents navigational challenges. Unlike planets, KBOs are small, often irregularly shaped, and move slowly through vast distances. Timing a rendezvous requires precision on the scale of kilometers over billions of kilometers of travel. Minor trajectory errors can lead to missing the target by millions of kilometers. Spacecraft must carry fuel reserves and maneuvering systems sufficient to correct course mid-flight. For humans, carrying enough fuel for course corrections along with life support and supplies multiplies the mass problem exponentially, creating near impossible engineering challenges with today's technology. Even with robotic precedents like New Horizons, the scale of Kuiper Belt exploration is staggering. Humans would need multi-decade mission planning, nuclear-powered propulsion, autonomous life support, radiation shielding, and extensive psychological preparation. Every mission must balance mass, speed, and sustainability in a way that no chemical rocket or conventional spacecraft can achieve today. The Kuiper Belt lies at the very edge of what is remotely feasible, a frozen frontier where humans may one day set foot, but only with breakthroughs in propulsion, shielding, and life support that have not yet arrived. The Oort cloud, humanity's farthest frontier. Far beyond the planets, beyond the icy rings of Neptune and the scattered icy worlds of the Kuiper Belt, lies a vast, almost unimaginably distant region of our solar system, the Oort cloud. This is not just a distant cluster of rocks or ice. It is a spherical shell surrounding the solar system, stretching trillions of kilometers from the Sun, a ghostly boundary between the familiar reach of human technology and the uncharted depths of space. No spacecraft has ever visited this region. No human has glimpsed it, and for now, it exists more as theory than observation. A place where the Sun's gravitational pull barely dominates, and where icy bodies drift through a vacuum colder than anything experienced in the inner solar system. The Oort cloud is thought to be home to trillions of icy bodies, from small comet nuclei a few kilometers across to larger objects tens or hundreds of kilometers in diameter. Its inner edge is roughly 2,000 astronomical units from the Sun, about 300 billion kilometers, while the outer edge could extend as far as 100,000 AU, or 15 trillion kilometers. To put that in perspective, Pluto, which lies at about 39 AU, is already almost unimaginable in distance for humans. The Oort cloud stretches orders of magnitude farther, essentially marking the theoretical edge of the Sun's influence, where interstellar space begins. With current propulsion, sending humans anywhere near the Oort cloud is completely beyond our lifetime. Even if we assume the fastest spacecraft ever launched, New Horizons, which traveled to Pluto at roughly 16 kilometers per second, we can do a rough calculation. At that speed, reaching the inner edge of the Oort cloud at 2000 AU would take about 30,000 years. To reach the outer edge, 100,000 AU, would take over 1 million years. Human lifespans, measured in decades, become infinitesimally small against this scale. Even accelerating spacecraft to double or triple that speed with current chemical or nuclear thermal rockets would barely make a dent in the timeline. Travel to the Oort cloud is not just difficult, it is a scale problem, one that cannot be solved without technologies that currently exist only in science fiction. Months in space for Mars missions already require careful recycling of oxygen, water and food, and strict radiation shielding. Years-long journeys push these systems to the extreme, but centuries or millennia. Current technology cannot sustain even a single human for more than a few years in space, let alone multiple generations. Even speculative ideas like generation ships, massive spacecraft in which people live, reproduce and die across multiple human generations, face enormous challenges. Shielding against cosmic radiation over centuries, maintaining food production, and repairing or replacing critical life support systems without resupply from Earth are problems that remain unsolved. Radiation is especially lethal. In the inner solar system, the Sun's magnetic field and heliosphere provide partial protection against galactic cosmic rays and solar particle events. By the time you reach the Oort cloud, the Sun's magnetic influence is weak, and shielding from the Sun itself is minimal. Cosmic rays and high-energy particles bombard any spacecraft continuously. For humans, exposure to these particles over decades or centuries without effective shielding would almost certainly be fatal. Even the most advanced materials or magnetic shielding concepts, which exist only in theory today, would have to function flawlessly for centuries. An engineering challenge that is staggering in scope. The sheer isolation of the Oort cloud also amplifies psychological challenges. Current Mars missions already deal with months of communication delay, with astronauts relying on stored routines and delayed guidance from Earth. In the Oort cloud, even radio signals take days, weeks, or months to reach Earth. Astronauts would be almost entirely cut off from any support. Any emergencies would have to be handled autonomously. Imagine dealing with medical crises, mechanical failures, or habitat malfunctions hundreds of billions of kilometers from the nearest human. The isolation is profound, and the stakes are life or death at every turn. Travel speed becomes a defining bottleneck. Chemical rockets, the mainstay of human spaceflight, are limited by the rocket equation. The more fuel you carry, the more fuel you need to carry the fuel, and so on. Even the largest proposed chemical rockets could not approach the speeds necessary to traverse the Oort cloud in a single human lifetime. Nuclear thermal propulsion could, in theory, double the speed of chemical rockets, and nuclear electric ion drives might provide sustained acceleration over years. But even these advanced concepts fall orders of magnitude short. To reach the inner Oort cloud in under a century would require propulsion capable of sustaining hundreds of kilometers per second for decades, a scale of engineering humanity has never approached. Energy requirements are equally daunting. A spacecraft large enough to sustain humans over centuries would need continuous power for life support, propulsion, heating, and communication. Solar power becomes negligible at the distances of the Oort cloud. Pluto already receives only 1/1600th the sunlight Earth does. Nuclear reactors could provide long-term power, but they would need to operate reliably for centuries without maintenance. Radioisotope thermoelectric generators, which power some deep space probes today, decay over decades and would be insufficient for a human colony. Essentially, sending humans to the Oort cloud would require self-sufficient, autonomous systems operating on a scale unmatched in engineering history. Fuel limitations are another hard boundary. Every kilogram of habitat, shielding, food or water adds to the total mass, exponentially increasing fuel requirements. For chemical rockets, the ratio of fuel to payload becomes astronomical, far beyond what could be launched from Earth. Nuclear propulsion helps, but even then, mass remains a severe constraint. The farther out you go, the more extreme these mass and energy requirements become. The physics simply cannot be bent. Chemical rockets cannot carry humans to the Oort cloud within a lifetime. And even advanced nuclear concepts require a level of precision, reliability, and longevity never before attempted. Robotic missions offer a glimpse of what might be possible. Voyager 1 and 2, after decades of travel, are now in interstellar space, approaching distances on the order of 150 AU from the Sun. They are uncrewed, powered by radioisotope thermoelectric generators, and carry no life support. Even at these modest distances, compared to the inner Oort cloud, travel has taken over 40 years. These spacecraft demonstrate the practical limits of current propulsion and show just how far humans would have to go to reach the outer edges of the solar system. Any crewed mission is orders of magnitude more difficult. Even the idea of multi-generational crews faces extreme challenges. Maintaining a human population over centuries requires stable habitats, renewable food sources, water recycling, artificial gravity to prevent muscle and bone atrophy, and robust psychological support. Every system must be repairable by humans on board without outside assistance, over timescales far longer than any spacecraft or life support system has ever been tested. Essentially, the Oort cloud is not a place humans could reach with current technology. It is a theoretical boundary, a scale test of what human engineering, biology, and endurance could ever achieve. Communication presents another bottleneck. Signals that take minutes to travel to Mars now take days or weeks at Oort cloud distances. Even a simple conversation with Earth would be impossible. Any feedback would arrive long after the event, requiring astronauts to make autonomous decisions for survival. Navigation also becomes increasingly difficult. Tiny gravitational influences from the Sun, planets, and passing stars could alter trajectories slightly, but over billions of kilometers, small deviations compound into massive errors. Trajectory corrections would need precise autonomous systems capable of functioning perfectly for centuries, a technological requirement far beyond current spacecraft design. The outer edge of the Oort cloud marks the transition to interstellar space. Gravity from the Sun barely holds sway, and the influence of nearby stars and the galactic environment increases. Any human mission reaching these distances would need to operate entirely independently from Earth, surviving in deep space where collisions with micrometeoroids, exposure to radiation, and extreme cold are constants. Even robotic probes, designed for longevity and efficiency, are limited. Voyager 1 and 2 have lasted over 40 years, but they operate at fractions of their original power, and their trajectories will take them past only a few dozen nearby stars over millions of years. Humans could not survive the same environment without revolutionary advances in propulsion, shielding, and life support. Proposals for reaching the Oort cloud are almost entirely theoretical. Concepts include nuclear propulsion, fusion drives, or even speculative antimatter engines capable of accelerating continuously for decades. These would need to maintain extreme reliability, with self-repairing systems and redundancy built in at every level. Even then, travel times are measured in centuries for the inner cloud, and millennia for the outer reaches. Current spacecraft technology is entirely inadequate for such missions. The Oort cloud serves as a boundary, a test of imagination and physics, where the limits of human reach are defined not by courage, but by propulsion, energy, and biology. The Oort cloud is also home to comets, potential resources, and mysteries about the formation of the solar system. Its icy bodies contain organic compounds, water ice, and other materials that may reveal the history of our cosmic neighborhood. Robotic missions could, in principle, collect samples and return data, but humans would be unlikely to participate directly. Even the fastest conceivable crewed spacecraft would take centuries to arrive, making human exploration effectively impossible within a normal human lifetime. Interstellar probes and the limits of human travel. Humanity has always looked up at the stars and imagined reaching them. We've built rockets, landed on the moon, sent humans to Mars in planning, and launched robotic explorers to the farthest planets in our solar system. But the moment you talk about going beyond the asteroid belt, leaving Mars far behind, venturing toward Jupiter, Saturn, Uranus, Neptune, or even the Kyper belt, the challenge explodes in scale. Travel times, life support, fuel requirements, and sheer distance become crushing limitations. And when you take that next leap into interstellar space, the distance is no longer measured in millions of kilometers, but in trillions, and human lifetimes fade to nothing in comparison. That's where interstellar probes come into the picture. One of the most ambitious plans in recent decades is Breakthrough Starshot, announced in 2016. The idea is simple in concept, but almost science fiction in execution. Tiny, ultralight spacecraft, essentially chips attached to light sails, accelerated to 20% the speed of light using powerful ground-based lasers. At those speeds, the probes could reach Proxima Centauri, the closest star to the Sun, in just over 20 years. That is the fastest any human-made object could travel outside the solar system with technology even remotely feasible today. Compare this to the Voyagers, which have been traveling for over 40 years and are still only 150 AU from the Sun, less than 0.003% of the distance to Proxima Centauri, and you start to grasp just how monumental the gap is between solar system travel and interstellar travel. Breakthrough Starshot is designed purely for robotic exploration. Each probe would weigh just a few grams, with no humans on board, no life support, no food or water, no oxygen. A human could never survive the acceleration, the radiation, or the near vacuum exposure of such a craft. And the acceleration itself is extreme. The lasers on Earth would push the sail to 20% the speed of light in minutes, producing forces that would instantly crush anything organic. That's why the program focuses on tiny chips. They carry cameras, sensors, and communication equipment, beaming back images and data across 4.24 light-years to Earth. Even at that distance, signals would take over 4 years to arrive, so instant communication is impossible. Human travel beyond Mars or the asteroid belt, even within the solar system, is already facing nearly insurmountable limits. Chemical rockets, the technology humanity has relied on since the 1960s, are fundamentally constrained by the rocket equation. The more mass you need to carry, the more fuel you must burn. And the more fuel you burn, the more fuel you need to lift that fuel. Launching humans beyond Mars requires not just propulsion, but massive supplies of food, water, oxygen, and radiation shielding. The farther you go, the more this mass multiplies, and the propulsion requirements grow exponentially. Take Jupiter, for example. It's roughly 628 million kilometers away on average. A chemical rocket could take a human crew there in 6 or more years. Saturn, at 1.2 billion kilometers, would take over a decade. The outer planets, Uranus and Neptune, would take decades, far longer than any astronaut could survive in current habitats. Even a flyby mission, where humans pass near a planet and return immediately, becomes dangerous. Travel times stretch to years. Exposure to cosmic radiation grows, and every system aboard the spacecraft must operate perfectly, with no chance for repair. Beyond the asteroid belt, distances and hazards increase exponentially. Microgravity for months or years leads to bone density loss, muscle atrophy, cardiovascular changes, and eye problems. Prolonged isolation causes psychological stress and, potentially, mental health crises. Radiation in deep space, outside Earth's magnetic field, becomes lethal over extended periods, especially near Jupiter's radiation belts. The technical and biological barriers multiply so fast that the idea of humans leaving Mars' orbit and venturing into the outer solar system is effectively impossible with today's rockets and life support systems. That's why interstellar missions are designed only for machines. Probes like Voyager 1 and 2, New Horizons, and the hypothetical Starshot craft can travel far beyond what humans could ever survive. Voyager 1, launched in 1977, is now over 23 billion kilometers from the Sun, moving at about 17 kilometers per second. Even at that speed, it will take tens of thousands of years to reach the nearest stars. Breakthrough. Starshot's design tries to address this problem by taking speed to an extreme, but only works for probes that weigh grams, not tons of crewed spacecraft. A human spacecraft moving at 20% the speed of light would require unimaginable amounts of energy, far beyond anything humanity can currently produce or store. The energy requirements alone are staggering. To accelerate even a modest human spacecraft to even 0.1% the speed of light, you would need hundreds of times more energy than the entire world consumes in a year. And that's before considering life support, shielding, and redundancy. Chemical rockets simply cannot scale to this level. Nuclear propulsion, whether thermal or fission electric, could potentially reduce travel times in the solar system. But even nuclear propulsion falls short for interstellar distances. Fusion or antimatter propulsion remain purely theoretical, decades or centuries away at minimum, and come with their own engineering nightmares, including safe containment, reactor longevity, and immense thermal management. Radiation is a major factor that Starshot neatly sidesteps, but humans cannot. In interstellar space, outside the Sun's protective heliosphere, cosmic rays and high-energy particles bombard spacecraft relentlessly. For tiny robotic chips, a few millimeters of shielding is sufficient, and failures don't cost lives. For humans, even brief exposure is dangerous, let alone decades in transit. Shielding to survive interstellar radiation would require enormous mass, which increases the propulsion problem exponentially. Every kilogram of protection adds fuel requirements, which adds more mass, which adds more fuel. The cycle quickly becomes unworkable with current technology. Communication is another barrier. For Starshot probes, light-speed communication already introduces multi-year delays. A human crew would be far more dependent on guidance, repair, and support. At a distance of 1 light-year, even if astronauts had perfectly functioning propulsion and life support, Earth would be invisible in real time. Commands, updates, or help would arrive years later. The autonomy required to survive alone in interstellar space is currently beyond human capability. We rely on constant feedback and support for even low-orbit missions. Remove that support for decades or centuries, and survival becomes near impossible. Even if we ignore life support, radiation, and energy, the sheer time factor kills the possibility. For a chemical rocket traveling to Alpha Centauri, the closest star at 4.24 light-years away, the journey would take tens of thousands of years. Starshot, using ultralight sails and powerful lasers, reduces that to a few decades, but again, it carries no humans. Scaling that up to accommodate life, food, water, and shelter multiplies the problem by orders of magnitude. Human interstellar travel remains entirely in the realm of theory, fantasy, or distant future speculation. Back in the solar system, even traveling beyond Mars presents extreme limits. The asteroid belt begins around 2.2 AU from the Sun, just beyond Mars. Beyond this belt lies the realm of Jupiter, Saturn, and the outer planets, where chemical rockets slow to impracticality and life support durations become extreme. Even assuming perfect propulsion, every mission beyond Mars exposes humans to long-term radiation, microgravity, and supply chain challenges that are currently unsolvable. A crewed mission to Jupiter or Saturn would be a decade-long ordeal with no margin for failure, and anything farther, Uranus, Neptune, Pluto, Kuiper belt objects, becomes a decades or centuries-long voyage, impossible to complete in a human lifetime. Breakthrough Starshot, in contrast, is a wake-up call for what is actually possible today. Tiny probes, traveling at a fraction of light speed, can reach other stars in decades and relay data back. This is the limit of current physics, applied with extreme ingenuity. Everything beyond that, humans leaving Mars, the asteroid belt, or even the Kuiper belt, runs into hard barriers: propulsion, energy, life support, radiation, and time. Even the most advanced nuclear concepts or speculative fusion engines cannot bring human interstellar travel into the realm of decades or a single lifetime. The reality check is stark. Humans are essentially limited to the inner solar system and perhaps Mars within the next century. Beyond that, we can dream, design, and simulate, but chemical rockets, nuclear thermal engines, and current life support technologies cannot take a human being to Jupiter, Neptune, or the stars. Robotic probes are our only ambassadors to the distant reaches of space. Voyager, New Horizons, and Starshot-type concepts will carry our curiosity and knowledge, but our bodies, as they exist now, cannot survive the distances, radiation, or time involved. Even planning for interstellar probes exposes the limitations of physics and engineering. The energy required for acceleration, the mass of shielding, the need for autonomous navigation and communication, and the challenges of surviving extreme environments all multiply as the distance increases. Every design constraint compounds, highlighting why humans cannot yet escape the solar system. The Breakthrough Starshot program is an elegant, almost poetic acknowledgement of these limits. Instead of bending physics to accommodate humans, we send robots at speeds we can achieve, carrying our curiosity and cameras, showing us the cosmos without risking life. Distance, time, and technology converge to form an almost unbreachable wall. Mars is within reach with chemical rockets. The asteroid belt stretches that reach, but still within decades of human travel. Jupiter and Saturn are conceivable with advanced nuclear propulsion, but the outer planets push timelines and logistics to impractical lengths. Beyond Neptune, the Kuiper belt, and certainly to interstellar space, human survival is simply not feasible today. The Breakthrough Starshot approach acknowledges this and works around it, giving us glimpses of the stars without attempting the impossible. Even with radical propulsion, fusion, antimatter, or laser-driven sails, the challenges of human survival, shielding, autonomous systems, and energy scaling multiply. The timeline of travel, exposure to radiation, isolation, microgravity, and system reliability all present problems that no existing technology can solve. Interstellar human travel remains, for now, a thought experiment, while robotic missions like Starshot represent the edge of what is actually achievable in our lifetimes. Robotic exploration allows us to extend human presence indirectly. Voyager 1, launched in 1977, continues beyond the heliosphere, now in interstellar space, carrying messages, cameras, and instruments, but no humans. Starshot is designed for speed and efficiency, sending tiny probes that could reach Alpha Centauri in decades. Humans, by contrast, are massive, delicate, and life support dependent. Travel times stretch to centuries. Fuel requirements grow beyond imagination, and radiation exposure becomes fatal. The gap between what robots can do and what humans can do is not just technological, it is almost absolute. Even imagining the future, interstellar human missions confront hard limits. The speed of light is a barrier, the mass energy problem, and the finite lifetime of human biology. Life support systems do not scale for centuries. Shielding for radiation becomes impossibly heavy. Energy requirements for propulsion and survival exceed the total energy humanity can currently generate. Communication delays stretch years or decades, making mission control useless. Navigation across trillions of kilometers becomes incredibly sensitive to minute errors. The reality is that the technology gap is enormous, and closing it would require breakthroughs we cannot currently predict. Beyond the solar system, interstellar travel. Humanity has reached the Moon, sent astronauts to orbiting stations, and rovers to Mars. We've launched robotic explorers to the far reaches of the solar system, past the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and even Pluto. Yet all of these achievements, as impressive as they are, exist within the gravitational influence of the Sun. Beyond that lies a void so immense that our current technology struggles to comprehend it: interstellar space, the territory between the stars. The closest star system to us, Proxima Centauri, sits 4.24 light-years away. That's about 40 trillion kilometers, or roughly 268,000 times the distance to Pluto. For context, even traveling at the speed of Voyager 1, humanity's fastest spacecraft with humans indirectly represented aboard through its instruments and messages, it would take over 70,000 years to reach that distance. Voyager 1, launched in 1977, serves as our reference point for what is physically possible today. It moves at roughly 17 kilometers per second, a speed that made it the fastest man-made object leaving the solar system. In over 40 years, it has only traveled a fraction of a light year. Voyager 2, traveling slightly slower, is still en route to interstellar space, but has taken nearly the same time to reach similar distances. These spacecraft are uncrewed, carrying instruments and golden records instead of life support systems, food, or oxygen. The challenges of scaling this speed and distance to human survival are staggering. Every kilogram added for life support, radiation shielding, propulsion or redundancy increases the mass exponentially, which in turn demands far more fuel or energy than even the largest rockets or nuclear engines can provide. Breakthrough Starshot, announced in 2016, represents humanity's first serious attempt to think beyond the solar system with realistic physics in mind. The concept is simple but radical. Tiny, ultra-lightweight probes, attached to reflective light sails, would be accelerated to roughly 20% the speed of light using ground-based lasers. At that velocity, the probes could reach Proxima Centauri in about 20 years, a time frame almost unfathomable compared to the decades-long journeys required to reach Mars or the outer planets. The catch? These probes are incredibly small, just grams in mass, and are designed to carry instruments, sensors, and communication equipment, but no humans. Accelerating a human-sized spacecraft to even a fraction of that speed with current propulsion technology is effectively impossible. The energy requirements, fuel mass, and life support needs explode beyond what humanity can generate or sustain. One way to put it in perspective is to consider the scale of energy involved. Accelerating a tiny chip with a light sail to 20% of light speed requires hundreds of gigawatts of laser power, concentrated precisely on a craft no bigger than a postage stamp. Doing the same for a human spacecraft, even with a crew of just a few people and minimal life support, would require energy equivalent to hundreds of times the total electricity consumption of Earth for an entire year, delivered continuously and with perfect precision. The physics of propulsion, combined with human needs, makes interstellar travel a problem of orders of magnitude beyond our current capabilities. Even ignoring energy requirements, the timeline itself is a massive barrier. A chemical rocket traveling at speeds achievable by today's best engines would take tens of thousands of years to reach the nearest star. Nuclear thermal rockets, an advanced concept that uses nuclear reactions to heat a propellant and generate thrust, could potentially double or triple the speed of a chemical rocket, but even then, the journey would take millennia. That's longer than recorded human history. Generationally, entire civilizations would rise and fall before a single spacecraft arrived at its destination. This is why scientists and engineers have had to imagine radical alternatives, including generation ships, cryogenic sleep, and AI proxies that could survive and explore autonomously while humans remain on Earth. Generation ships are an idea that has fascinated scientists and sci-fi writers alike. The concept is a massive spacecraft designed to house multiple generations of humans over centuries or even millennia. Crew members would live, age, reproduce, and die aboard the ship while their descendants continue the journey. In theory, this could allow humans to travel to Proxima Centauri without the impossible requirement of multi-century individual lifespans. But the engineering challenges are staggering. The ship must provide food, water, oxygen, and waste recycling for hundreds or thousands of people over centuries. Systems must be fully autonomous and repairable by onboard crews with no hope of Earth-based resupply. Shielding against cosmic rays, micrometeoroids, and solar particle events must last for generations without failure. Even small mechanical failures could compound over centuries into catastrophic problems. The social and psychological aspects are equally daunting. Human societies have never been isolated in closed environments for more than a few years at a time. Imagine centuries in isolation from the rest of humanity. Cryosleep or suspended animation is another theoretical solution. If humans could be placed in a state of suspended biological activity, metabolism slowed to near zero, it would reduce the need for food, water, and oxygen, dramatically decreasing mass requirements for interstellar travel. However, no technology currently exists to safely induce cryosleep for extended periods, let alone centuries, while maintaining brain and organ function. radiation exposure remains a deadly problem. Even if metabolism could be paused, every passing cosmic ray and high-energy particle would strike the body relentlessly, potentially causing DNA damage that no medical intervention could repair in transit. AI proxies represent a more plausible near-term approach. Instead of sending humans, advanced autonomous machines could travel across light years, exploring, analyzing, and reporting data back to Earth. These proxies could operate for decades or centuries, repairing themselves with onboard systems, adapting to unforeseen challenges, and gathering information from interstellar space. Breakthrough Starshot is an example of this philosophy, a tiny autonomous probe racing towards another star at incredible speed, sending back data while humans remain safely on Earth. This approach sidesteps the impossible biological and psychological challenges, focusing on what is feasible within physics and technology. When comparing a lifetime-limited mission to interstellar distances, the contrast is staggering. A human lifetime, even stretched with generational approaches or cryosleep, is measured in decades. Interstellar distances are measured in light years, each equal to roughly 9.46 trillion kilometers. The nearest star, Proxima Centauri, is 4.24 light-years away, meaning even a light-speed journey would take over 4 years. At the speeds of the fastest rockets we have today, the journey stretches to tens of thousands of years. For all practical purposes, humans cannot personally traverse these distances within a single lifetime. The physics of distance, speed, energy, and biology are not negotiable. Even within our own solar system, the scaling of challenges hints at the difficulty. A mission to Mars takes months and already pushes the limits of current life support and radiation shielding. The asteroid belt takes years. Jupiter and Saturn take decades. Beyond Neptune and into the Kyper belt, we face decades-long voyages that test the boundaries of human endurance and engineering. Interstellar space is an entirely different scale, where distance multiplies every problem by thousands. Every kilogram of food, water, shielding, or fuel becomes a monumental barrier. And even the fastest imaginable propulsion cannot bring humans there in a lifetime. Current proposals for human interstellar travel, therefore, exist almost entirely in the realm of theory. Fusion drives, antimatter engines, and other speculative propulsion systems promise immense speeds, potentially a few % of light speed, but none have been realized. Each comes with engineering nightmares, from safely containing massive energy reactions to maintaining stability and control over decades. Even if these engines could exist, the radiation, microgravity, life support, and human psychology challenges remain unsolved. The sheer scale of travel across trillions of kilometers requires autonomous systems, redundancy, and a level of reliability humanity has never built. Voyager 1 and 2, though uncrewed, offer a tangible benchmark. Voyager 1 has traveled over 23 billion kilometers, leaving the solar system and entering interstellar space. At this speed, reaching Proxima Centauri would take over 70,000 years. New Horizons, traveling faster than Voyager, would still require over 50,000 years to reach the nearest star. Breakthrough Starshot compresses this timeline to decades, but only because it sacrifices mass, sending tiny chips rather than humans. Any human-equivalent mission would require propulsion, shielding, and life support many orders of magnitude beyond what we currently possess. The limits are clear. Even with perfect engineering, humans traveling beyond the asteroid belt and into interstellar space are restricted by the combination of distance, speed, energy, and biology. Generational ships or cryosleep remain purely theoretical, and AI proxies or miniature probes are the only viable near-term solutions. Breakthrough Starshot demonstrates this principle beautifully, showing how humanity can reach the stars indirectly, sending data and exploration while remaining safely on Earth. Human travel to another star in a single lifetime with current technology or even near-future concepts is effectively impossible. Every problem compounds: energy for propulsion, shielding against cosmic radiation, autonomous operation over decades or centuries, life support for generations, psychological well-being of isolated crews, navigation across trillions of kilometers, and the simple, unchangeable reality of human lifespan. Each factor alone is daunting. Together they form a wall that humanity cannot currently overcome. Breakthrough starshot, fusion drive concepts, and antimatter propulsion represent the ingenuity required to think beyond the solar system, but they also starkly illuminate the limitations of human travel. Physics and biology set hard boundaries. Even if humanity were able to engineer a propulsion system capable of sustaining significant fractions of light speed, other challenges persist. Energy generation and storage for onboard life support, radiation shielding that can protect humans from galactic cosmic rays, navigation systems precise over trillions of kilometers, and repairable autonomous systems capable of functioning over centuries are all necessary. Any failure in one subsystem over decades could doom a mission. For starshot-like probes, failure is inexpensive. For humans, it would be fatal. Beyond the stars' human limits and the future of interstellar travel. We've seen how humans cannot reach Proxima Centauri or any nearby star in a single lifetime with current technology. But scientists, engineers, and dreamers have been building concepts for how humans might someday leave the solar system, even if it takes centuries or relies on radical new technologies. This is where generational ships, cryosleep, fusion drives, antimatter engines, and AI proxies enter the conversation, each representing a potential bridge between what is possible today and what could someday be reality. Let's start with generational ships, probably the most iconic idea for interstellar human travel. Picture a massive spacecraft, a self-contained city hurtling through space, designed to carry hundreds or even thousands of people across decades or centuries. The idea is simple. Humans board the ship, live, work, age, and reproduce over multiple generations, with each new generation continuing the journey toward a distant star. In theory, a generation ship could make the 4.24 light-year trip to Proxima Centauri. But the logistics of such a journey are mind-bending. Every system on the ship, from air and water recycling to food production, waste management, energy generation, and even social structure, must be perfectly engineered to function autonomously for hundreds of years. Food production alone is a monumental challenge. Hydroponics or aeroponics could theoretically sustain crops in a closed environment, but over centuries, crops must reproduce without failure, pests or diseases must be prevented, and nutrient recycling must be flawless. Any disruption could lead to catastrophic shortages. Water and oxygen systems must also operate continuously, cycling resources efficiently with no chance of failure. Mechanical systems wear down over time, electronics degrade, and metals fatigue. The ship must include robust redundancy and repair systems, with crew members trained to fix virtually any problem without external help. One broken air pump or failing power system could jeopardize the entire mission. Radiation shielding is equally critical. Outside the protective bubble of Earth's magnetosphere, cosmic rays and solar particle events become deadly. A generation ship traveling at even a fraction of light speed would face decades or centuries of bombardment from high-energy particles. Shielding against this radiation adds mass, which in turn requires exponentially more fuel or energy to accelerate the ship. Even theoretical designs using thick layers of water, hydrogen, or specialized materials must be engineered to function for hundreds of years without failure. There is no margin for error. The longer the journey, the greater the cumulative risk. Humans are social animals, and life in an isolated, confined environment for generations would test the limits of human resilience. Generations born aboard the ship would never see Earth, experiencing a life completely removed from the planet of their ancestors. Governance, conflict resolution, education, and culture would all have to be carefully planned to prevent social collapse. Even small disagreements could escalate over decades, threatening the mission. Ensuring the mental and emotional well-being of generations living in such isolation is as critical as managing oxygen or power systems. cryosleep or suspended animation offers an alternative to multi-generational life. If humans could be placed in a state of deep hibernation for decades or even centuries, it would dramatically reduce resource requirements. Food, water, and oxygen needs would drop, and the spacecraft could be smaller and lighter. The catch is that cryosleep technology for long durations does not exist today. Current research on hibernation in animals shows promise, but humans are far more complex. The body's organs, muscles, and brain require constant care, and even minor metabolic disturbances during hibernation could lead to irreversible damage. Radiation protection remains a problem. Frozen humans would still accumulate DNA damage from cosmic rays unless the ship's shielding is near perfect. Fusion propulsion is one of the more realistic concepts for near-future interstellar travel. Fusion engines could provide continuous acceleration over months or years, eventually achieving speeds approaching a significant fraction of the speed of light. Unlike chemical rockets, which burn fuel quickly and then coast, fusion engines could, in theory, sustain thrust for long periods, drastically shortening interstellar travel time. Designs like Project Daedalus in the 1970s and more recent fusion concepts imagine ships propelled by controlled fusion reactions, using helium-3 or deuterium as fuel. Even then, to reach Proxima Centauri, travel would take decades, and the ship would have to maintain flawless operation for the entire journey. Shielding, life support, and energy management all scale exponentially with mass, making such a mission incredibly complex. Antimatter propulsion takes the idea even further into theoretical extremes. Antimatter reactions release millions of times more energy per kilogram than chemical fuel, meaning that, in theory, a small amount of antimatter could propel a human spacecraft to a significant fraction of light speed. But antimatter production today is minuscule. Atoms of antimatter are produced only in particle accelerators and at immense cost. Containing and controlling antimatter safely is a monumental challenge. Even tiny leaks could destroy a spacecraft instantly. While antimatter propulsion offers the potential for interstellar travel within a human lifetime, the engineering hurdles are astronomical, and practical implementation remains decades, if not centuries, away. AI proxies and robotic missions are already a reality, and they demonstrate how humanity could explore interstellar space without physically being present. Starshot-style probes, tiny and extremely lightweight, can be accelerated to 20% of light speed using powerful lasers on Earth. They could reach Proxima Centauri in about 20 years and transmit data back. These probes sidestep the impossible biological and resource challenges faced by humans. Autonomous AI spacecraft could operate for decades, repairing themselves, navigating, collecting data, and adapting to unforeseen challenges. For interstellar exploration, AI may be the only viable path for centuries, while human travel remains purely conceptual. Even with AI or robotic probes, the limitations are enormous. Communication across light years is inherently delayed. Signals traveling at light speed from Proxima Centauri take over 4 years to reach Earth. Any mission beyond a few light years must operate autonomously, making critical decisions without human input. Precision navigation is essential. Minor deviations over trillions of kilometers compound into massive errors. Probes must be incredibly durable, able to survive radiation, micrometeoroids, and thermal extremes. These challenges are manageable with small, unmanned craft, but for humans, the stakes become fatal. Now consider what a lifetime-limited human mission would look like. Even the nearest star, Proxima Centauri, is so far that it is beyond a human lifetime, with current or near-future propulsion. Chemical rockets could never get there. Nuclear or fusion propulsion might reduce travel times to decades, but still exceed a single human lifespan for crewed missions, unless combined with generational ships or cryosleep. Essentially, a human crew would never personally experience the stars. The journey would span generations, leaving only indirect participation for the first travelers. Unlike robotic probes that can transmit data back quickly, humans are constrained by biology and logistics, which fundamentally limits our reach. Travel times, energy needs, and resource requirements all scale exponentially with distance. For Proxima Centauri, even at 10% of light speed, the journey would take over 40 years, longer than the average human career, requiring extraordinary engineering and psychological resilience. At the same speed, shielding from cosmic radiation would need to be continuous and perfect for the entire journey. Any breakdown could be catastrophic. Life support systems would need unprecedented redundancy. Navigation would require autonomy, as Earth-based corrections would take years to arrive. Essentially, the further we try to go, the less a single human lifetime can accommodate. These challenges are magnified for more distant stars. Alpha Centauri A and B, Barnard's star, Wolf 359, and other nearby stars lie within 10 light-years. But beyond that, travel times expand to centuries or millennia, even with speculative propulsion systems. The energy required to accelerate a crewed ship to a significant fraction of light speed becomes unimaginable. The psychological and social strain on a multi-generational crew compounds. Maintenance and repairs must last longer than any technology humans have built. The limits of human physiology become hard boundaries. Life beyond the solar system for humans, within a single lifetime, is effectively impossible. Even if breakthroughs occur, fusion propulsion, antimatter engines, or advanced cryosleep, interstellar travel remains a massive challenge. Breakthrough Starshot shows what is possible without humans. Rapid travel to another star with minimal mass, gathering data and sending it home. Crewed interstellar missions remain orders of magnitude beyond our capabilities. AI proxies, autonomous systems, and miniature probes will likely be humanity's first ambassadors to other stars. Any attempt to send humans beyond Mars, let alone the asteroid belt or into interstellar space, faces nearly insurmountable obstacles. Energy, mass, life support, radiation, psychology, and time all collide to form a wall that cannot currently be breached. Interstellar travel also highlights the difference between what is theoretically possible and what is realistically achievable. Physics allows us to imagine near light-speed travel, antimatter engines, or generation ships, but engineering, biology, and human limitations set hard boundaries. Distance is unforgiving. Time stretches across centuries or millennia. Energy requirements explode. Systems must function autonomously for periods far beyond human experience. Radiation will relentlessly bombard the spacecraft. Even the smallest errors, compounded over light years, can ruin the mission. The gap between imagination and reality is vast, and today, robotic proxies remain the only bridge across this gulf. Humanity's curiosity drives these ideas. We dream of leaving the solar system, visiting other stars, and seeing what lies beyond the nearest points of light in the sky. Yet, for the foreseeable future, all crewed travel remains limited to the inner solar system. Proxima Centauri, Alpha Centauri, Barnard's star, Wolf 359. These will be observed, studied, and analyzed by autonomous probes, light sails, and AI systems. Humans will guide, design, and monitor, but we will remain physically tethered to Earth's neighborhood. Starshot-style missions, fusion-propelled probes, and even futuristic concepts like antimatter engines will allow us to reach other stars in data and images. But the human body, fragile and resource-intensive, is constrained to a tiny bubble of space relative to the vast universe. Even thinking about generation ships or cryosleep emphasizes one critical point. Interstellar travel is not simply about building a faster rocket. It is about engineering entire self-contained ecosystems, capable of sustaining human life over centuries, while maintaining perfect shielding, autonomy, and energy systems. It is about preparing humans to survive without Earth for generations, isolated in a tiny spacecraft. Every element, food, water, oxygen, energy, propulsion, radiation protection, navigation, social structure, mental health, must operate flawlessly for decades or centuries. The scale of the challenge is almost incomprehensible. For now, the closest humans can realistically reach is Mars, and perhaps the asteroid belt in extended missions. The outer planets may be possible with decades-long journeys, but interstellar distances are effectively out of reach. The physics of speed. How fast can we really go? When you look up at the night sky, it's easy to forget just how vast space is. Even our fastest spacecraft move at a crawl compared to the distances between stars. To understand what humans can actually achieve in a lifetime, we have to start with the basics. How fast can we go? Speed in space isn't just a number. It's a game of physics, engineering, and biology. Every jump in velocity comes with exponential increases in energy requirements, structural demands, and human risk. The first concept we need is escape velocity. This is the speed needed to break free from a planet's gravitational pull without using continuous propulsion. For Earth, escape velocity is roughly 11.2 kilometers per second, about 40,000 kilometers per hour. Achieving this speed is what allows rockets to leave Earth orbit and begin interplanetary travel. It's why Saturn V rockets could send Apollo missions to the Moon, and why SpaceX's Falcon Heavy can reach the edge of the solar system for interplanetary probes. But escape velocity is only the beginning. Once you leave Earth, you are in orbit around the Sun, and traveling to other planets or other stars requires even more speed to break free from the Sun's gravitational influence. That number jumps to over 42 kilometers per second, already beyond anything chemical rockets alone can maintain continuously. Chemical rockets, the engines that launched humans to the Moon, have a hard speed limit. They work by burning fuel to expel mass at high speed, using Newton's third law. For every action, there's an equal and opposite reaction. The faster you want to go, the more fuel you must carry, and the more fuel you carry, the heavier the rocket becomes. This is the famous rocket equation, which makes it almost impossible to scale chemical rockets for interstellar travel. Even if you built a chemical rocket as big as a city, it would only achieve a fraction of the speed required to reach another star in a human lifetime. For context, Voyager 1, humanity's fastest spacecraft relative to the Sun, moves at 17 kilometers per second. That's fast for humans, but infinitesimal on the scale of light years, requiring over 70,000 years to reach Proxima Centauri. This is where hypothetical propulsion methods come into play. Scientists have long studied alternatives that could break the speed barriers chemical rockets cannot. One concept is nuclear thermal propulsion, which uses nuclear reactions to heat a propellant and expel it at much higher speeds than chemical rockets. Nuclear thermal engines could, in theory, double or triple current spacecraft velocities, cutting interplanetary travel times from years to months. For instance, Mars missions that take 6 to 9 months with chemical rockets could potentially shrink to 3 to 4 months using nuclear thermal engines. But even nuclear propulsion falls short for interstellar journeys. Reaching a nearby star within a human lifetime still requires speeds close to a significant fraction of light speed, far beyond what nuclear thermal engines can achieve. Ion drives are another breakthrough in theoretical and experimental propulsion. Unlike chemical rockets, ion engines don't rely on burning fuel rapidly. They use electricity to accelerate ions to incredible speeds over long periods. NASA has already used ion propulsion for missions like Dawn, which explored Vesta and Ceres in the asteroid belt, and Deep Space One, which tested advanced technologies. Ion engines produce low thrust, but can operate continuously for years, slowly accelerating a spacecraft to high speeds. The key advantage is efficiency. Fuel mass is minimal, but the downside is acceleration is so gradual that even decades of operation might not bring a human crew close to interstellar velocities. Even more exotic are antimatter engines. Antimatter is the mirror opposite of normal matter. When they collide, they annihilate each other, releasing 100% of their mass as energy, compared to less than 1% for chemical reactions. In theory, antimatter propulsion could accelerate a spacecraft to a significant fraction of light speed. But producing and storing antimatter safely is currently beyond human capability. Particle accelerators can make a few atoms at a time, but to fuel a single human-sized spacecraft would require kilograms, which is millions of times more than what humanity can currently produce. Even if we solved the engineering problem, the energy and shielding requirements for humans at those speeds are staggering. Speaking of humans, acceleration itself poses profound physiological challenges. The human body is designed to survive a few G-forces, gravity equivalents experienced during takeoff or rapid maneuvers. But sustained acceleration at high multiples of G can crush organs, collapse blood vessels, and damage the skeleton. For chemical rockets, acceleration is brief and managed with careful engineering and seating orientation. For hypothetical high-speed drives like ion, nuclear, or antimatter engines, acceleration over months or years would need to be extremely low, fractions of a G, to prevent long-term damage. That introduces a paradox. Humans can't withstand extreme acceleration, yet slow acceleration means the trip takes even longer. Designing a spacecraft for both speed and human survival is an unsolved problem. Now let's introduce special relativity, the physics that governs extreme speeds near light. Albert Einstein's equations show that as an object approaches light speed, time itself begins to slow down relative to an outside observer. This is time dilation, a concept often dramatized in science fiction. For astronauts traveling at 90% the speed of light toward a nearby star, decades of travel could feel like years on board, while decades pass on Earth. In principle, relativistic travel could allow humans to shortcut the passage of time, but achieving even 10% light speed with a crewed spacecraft remains far beyond current or near-future propulsion. The energy required grows exponentially as speed increases, and radiation exposure, shielding, and structural integrity become critical limits. Even in theoretical scenarios, relativistic speeds introduce new dangers. At near light speed, cosmic dust and micrometeoroids, usually harmless, become lethal projectiles. Hitting a grain of sand at 90% light speed could release energy equivalent to a small nuclear explosion. Shielding against these impacts would require heavy armor, which in turn increases the mass, fuel requirements, and engineering complexity. Radiation from the interstellar medium also intensifies. Moving at relativistic speeds transforms low-energy particles into high-energy radiation that could penetrate any shielding short of massive, impractical thickness. The faster you go, the harsher the environment. Recent breakthroughs in propulsion research, however, are encouraging, at least for unmanned probes. Laser-driven light sails, like the breakthrough Starshot concept, could accelerate gram-sized spacecraft to 20% of light speed. The principle is elegant. A powerful Earth-based laser focuses light on a reflective sail, gradually pushing it to incredible velocities. Within minutes, the probe could reach 60,000 kilometers per second, far faster than any chemical or nuclear rocket. This demonstrates that near-light speed travel is physically possible, but only for ultra-lightweight, uncrewed spacecraft. Scaling this up to a human-sized craft with life support, shielding and supplies is a problem orders of magnitude more difficult. Another research avenue is magnetically accelerated plasma drives or fusion propulsion, which combine theoretical physics with high-energy engineering. Fusion propulsion could, in theory, allow sustained thrust over years, slowly accelerating a spacecraft to 10–20% of light speed. Projects like Daedalus, proposed in the 1970s, imagined sending a robotic probe to Barnard's star using fusion drives, accelerating small payloads to interstellar distances in decades. While still speculative, fusion propulsion represents a tangible step beyond chemical rockets, offering a bridge toward eventual interstellar exploration, at least for unmanned craft. Let's take a step back and contrast speeds. Chemical rockets can barely escape the sun's gravity at 42 kilometers per second. Ion engines push spacecraft to hundreds of kilometers per second over decades. Nuclear thermal could reach thousands of kilometers per second. Breakthrough Starshot's lasers could reach tens of thousands of kilometers per second. Light speed travel remains theoretical, and even approaching 10% of light speed requires energy and engineering far beyond current capabilities. The gap between interplanetary and interstellar velocities is enormous, and human biology is the first hard limit that engineers cannot bypass. Acceleration also interacts with microgravity. Sustained high acceleration could act like artificial gravity, helping mitigate bone and muscle loss over long missions. Low acceleration, while safer, leaves humans in prolonged microgravity, causing long-term health effects. This tension between safe acceleration, human physiology, and the need for speed shapes every consideration for interstellar travel. A human crew cannot endure months or years of G-forces beyond what the body can tolerate, and slow acceleration stretches travel times to centuries, making a single lifetime journey impossible. Radiation again becomes the silent enemy. Cosmic rays, solar particle events, and interstellar medium particles bombard any spacecraft leaving the solar system. At low speeds, shielding is manageable with layers of aluminum, water, or hydrogen-rich materials. At near light speed, even tiny particles impact with relativistic energy, potentially vaporizing spacecraft material and penetrating crew compartments. This means that the faster you try to go, the harsher the environment becomes. A brutal paradox for any mission beyond the solar system. Special relativity introduces one more wrinkle. Energy requirements grow as you approach light speed. Mass increases relativistically, meaning a spacecraft requires more and more energy to continue accelerating. Even the theoretical antimatter engine, if perfectly efficient, would require unimaginable quantities of fuel to push a human mass spacecraft to 50% of light speed. The laws of physics themselves impose a ceiling. No matter how advanced the engine, you cannot exceed light speed. And every approach to it increases energy requirements exponentially. Recent experimental breakthroughs hint at possible pathways. Laser propulsion experiments, plasma drive tests, and small-scale fusion experiments show that high-efficiency, long-duration propulsion is not science fiction. It is engineering on the cutting edge. NASA, ESA, and private companies like Breakthrough Initiatives are exploring these possibilities, often focusing on small, unmanned craft first. These experiments are vital because they scale knowledge. Understanding propulsion physics, laser focus, and plasma dynamics at small scales allows engineers to imagine what might one day be possible for larger craft, though human missions remain far off. Even the concept of near light speed human travel remains constrained by human biology, energy limits, shielding requirements, and structural integrity. Generational ships or cryosleep remain theoretical, while robotic probes continue to lead the way. For now, the physics of speed serves as both a guide and a boundary. It shows us what is achievable today, hints at what may be possible with future breakthroughs, and clearly delineates the limits of human survival in high-velocity space travel. Achieving extreme velocities in space is not just about building a better engine. It's a battle against energy, biology, time, and the unforgiving void of interstellar space. From cryogenic chambers to laser-driven sails, scientists are experimenting with ways to stretch the limits of speed while keeping humans alive, or at least keeping humanity's influence alive through unmanned proxies. The physics of speed pushing human limits. Let's begin with practical applications of nuclear and fusion propulsion. Nuclear thermal engines, in which a reactor heats a propellant to incredible temperatures, could, in theory, accelerate a spacecraft to tens of kilometers per second over months. Unlike chemical rockets, which burn fuel explosively and coast, nuclear engines provide continuous thrust, meaning spacecraft could gradually leave the solar system faster than anything humans have launched so far. NASA's NERVA program in the 1960s and 70s tested nuclear thermal propulsion designs capable of pushing crewed Mars missions from 9 months to perhaps 3-4 months. Beyond Mars, the same engines could allow missions to Jupiter or Saturn to shrink from years to a few months. But scaling these systems to interstellar distances becomes tricky. Fuel requirements rise dramatically, and radiation shielding must protect humans from both the onboard reactor and interstellar cosmic rays. Every kilogram of shielding increases the mass, which in turn demands more fuel or power. It becomes a chain reaction of engineering constraints. Fusion propulsion offers even more tantalizing possibilities. By harnessing controlled fusion reactions, Spacecraft could theoretically achieve speeds approaching 10 to 20% of light speed, sufficient to reach the nearest stars in decades. Concepts like Project Daedalus, designed in the 1970s, imagined sending robotic probes to Barnard Star using helium-3 fusion engines, accelerating small payloads to interstellar velocities. The advantage of fusion is that it provides continuous thrust over long periods, unlike chemical rockets that burn out quickly. Yet fusion engines for humans would need enormous shielding, energy management systems, and life support capable of surviving decades of near-constant acceleration. It's technically possible, but every system must operate flawlessly for years. Antimatter propulsion pushes the envelope even further. In antimatter reactions, matter and antimatter annihilate completely, releasing energy millions of times more powerful per kilogram than chemical fuel. In theory, this could accelerate a spacecraft to a substantial fraction of light speed, but antimatter is extraordinarily rare and difficult to produce, and storing it safely is a nightmare. Any leakage could instantly destroy a spacecraft. Even if we solved production and containment, the shielding for humans traveling at such speeds would be enormous. Cosmic particles at relativistic velocities strike with catastrophic energy, turning every dust grain into a lethal missile. Human biology becomes the limiting factor even before fuel or propulsion. Speaking of humans, acceleration and g-forces remain a major constraint. Continuous high acceleration can crush organs, impede blood flow, and damage bones and muscles. Chemical rockets manage this by limiting acceleration to tolerable levels and seating astronauts to distribute forces evenly. For futuristic propulsion like nuclear, fusion, or antimatter, sustained acceleration must be very low, fractions of a g, over months or years. This introduces another paradox. Slow acceleration keeps humans safe, but slow acceleration also stretches travel times to decades or centuries. The physics of speed and the limits of biology are locked in a brutal trade-off. One way around prolonged acceleration is artificial gravity via rotation. Spacecraft could use centrifugal force, spinning habitats like giant wheels, to simulate gravity while accelerating slowly. This would reduce muscle and bone loss over decades-long journeys. However, rotating habitats introduce engineering complexity. Rotation must be perfectly balanced, the structure must withstand stresses, and navigation and docking become more complicated. On an interstellar mission, even minor engineering miscalculations could become fatal over decades. Now, let's dive into time dilation, the relativistic effect that makes near-light speed travel so fascinating. As spacecraft approach light speed, time slows for the travelers relative to Earth. For example, a crew traveling at 90% the speed of light toward Proxima Centauri would experience a journey that might feel like 5 years on board, even though over 4 years pass on Earth. In theory, relativistic travel allows humans to shortcut the passage of time, making long trips tolerable within a lifetime. But achieving 90% of light speed is far beyond current technology for a human crew. Every attempt to push closer to light speed increases the energy required exponentially and magnifies all other risks, from radiation to structural integrity. Time dilation is fascinating in theory, but remains practically unreachable for crewed missions with today's technology. Radiation at high velocities is another invisible killer. Cosmic rays and interstellar particles, normally harmless at low speeds, become relativistic projectiles at near light speed, capable of penetrating any ordinary shielding. Even traveling at 10% of light speed, the cumulative radiation dose over decades would be lethal without thick, heavy shielding, adding hundreds or thousands of tons of mass to any human spacecraft. Every kilogram for shielding requires fuel to accelerate, creating an engineering cascade that quickly becomes unmanageable. Cryogenic sleep or suspended animation offers a hypothetical solution to human limits. If humans could hibernate for decades, resource needs would drop dramatically, and the ship could remain smaller and lighter. Research in animals has shown promising results. Some mammals can lower their metabolic rates to survive months with minimal energy. Extending this to humans could, in theory, allow centuries-long voyages. But humans are far more complex, and the effects of prolonged cryosleep on the brain, organs, and immune system are unknown. Radiation shielding remains necessary, and every malfunction could be fatal. Cryosleep may eventually be part of the human interstellar toolkit, but for now, it remains speculative. Meanwhile, AI proxies and unmanned probes are already demonstrating what's possible. Tiny starshot-like probes could reach Proxima Centauri in about 20 years, transmitting data back to Earth. Autonomous AI spacecraft can navigate, adapt, repair themselves, and collect information in ways humans cannot. They avoid the biological constraints, radiation issues, and life support challenges that make interstellar crewed travel so difficult. In many ways, unmanned probes are humanity's first true ambassadors to the stars, able to explore regions that would kill any human passenger in minutes. Even small unmanned missions face challenges. Navigation over trillions of kilometers must be precise. Tiny trajectory errors compound into massive deviations. Communication delays span years. High-speed interstellar travel turns even tiny dust grains into lethal projectiles. Energy management, autonomous repair, and long-term data storage are critical. But unlike humans, these probes are not limited by lifespan or biology. They illustrate how speed and distance intersect with physics. Reaching other stars is a problem of energy, navigation, and resilience, rather than human endurance. Let's put this all into perspective. Chemical rockets can reach tens of kilometers per second, nuclear engines potentially hundreds, ion engines hundreds to thousands over long periods, and laser sails can accelerate tiny probes to tens of thousands of kilometers per second. Time dilation theoretically allows near-light speed travelers to experience shorter durations, but human missions are limited by biology, shielding, acceleration, and energy. Every increment of speed introduces exponential engineering challenges. Humans may never reach even the nearest stars without multi-generational missions or suspended animation. AI probes demonstrate that exploration is possible, but human physical presence remains tethered to the inner solar system for now. Recent breakthroughs are exciting but incremental. Experiments with plasma drives, ion engines, laser sails, and fusion concepts show that high-speed travel is physically possible. The challenge is scaling these technologies for human use. Energy requirements remain the single greatest barrier. Propelling a spacecraft with humans aboard to 10% of light speed would require more energy than humanity currently produces in a year. Radiation shielding and life support further multiply mass and complexity. Even the best theoretical engines, fusion or antimatter, must operate flawlessly for decades or centuries. Any system failure at high speed could be catastrophic. The bottom line is this: speed in space is a multi-dimensional challenge, not a single number. It's energy, fuel, acceleration, shielding, life support, radiation protection, and human biology all combined. We understand the physics. We know what is required. What we don't have is the technology, energy infrastructure, or biological resilience to achieve interstellar speeds for humans. Every breakthrough pushes the envelope, but the gap between unmanned probes and crewed missions remains immense. So when thinking about the physics of speed, we must consider not just velocity, but acceleration, sustainability, human tolerance, and relativity. Humans may one day push Mars or the outer planets within months or years, but reaching another star within a single lifetime remains a theoretical exercise. AI probes, laser sails, and fusion experiments represent humanity's first real steps into interstellar space, while crewed missions remain tethered to the hard limits of energy, physics, and biology. Every increase in speed compounds the problems. Radiation intensifies, shielding grows heavier, energy needs soar, and even minor system failures become fatal. In a lifetime-limited human context, speed is as much a biological constraint as a technological one. Rockets can go faster, engines can be more efficient, and lasers can accelerate tiny probes to near-light speed. But human bodies are fragile. Acceleration must remain low, radiation must be blocked, life support must function continuously, and structural integrity must be maintained for decades. Even relativistic time dilation offers no practical shortcut without unattainable velocities. Humanity's physical presence is bound by these limits, while our ambition to explore continues to expand through machines and imagination. Human limits, the lifetime factor. Imagine looking up at the night sky and realizing that even with our fastest rockets, the stars aren't just far, they're practically unreachable in a human lifetime. That's the reality of space exploration. The universe isn't measured in kilometers or miles. It's measured in millions, billions, even trillions of kilometers. For humans, our lifespan, the time we have from birth to death, is the ultimate boundary. It sets a natural limit on how far we can travel, and no amount of ambition can erase that fact. Let's start with the obvious. Humans have a finite lifespan. The average human today lives roughly 70 to 80 years, depending on the country. Even pushing for the exceptional, people living past 100. The time available to leave Earth, accelerate to extreme speeds, navigate through space, and return safely is incredibly short. Space travel isn't like getting in a car and driving across a continent. Distances are vast, and the laws of physics place strict limits on speed and energy. Traveling beyond Earth orbit requires rockets that can reach tens of thousands of kilometers per hour, and even the fastest spacecraft we've ever launched take months or years to reach other planets in the solar system. Take Mars, for example. At its closest approach, Mars is about 55 million kilometers from Earth. With current chemical rockets, a one-way trip takes 6 to 9 months, depending on orbital alignment. That's manageable in a human lifetime. But once you try to go further, distances explode. Jupiter is roughly 778 million kilometers away, Saturn nearly 1.4 billion kilometers, and Neptune lies at 4.5 billion kilometers from Earth. Even at constant high speed, the time required to travel these distances starts to rival decades. The farther you go, the more your lifespan becomes the real limit, not fuel, engineering, or even willpower. Speed is central to the lifetime factor. A spacecraft's velocity determines how much distance a human can realistically cover. Chemical rockets, like the Saturn V that carried Apollo astronauts to the Moon, can achieve tens of kilometers per second relative to Earth, but leaving the solar system requires even higher velocities. Voyager 1, humanity's fastest human-made object, travels at about 17 kilometers per second relative to the Sun. That's 61,200 kilometers per hour. At that pace, reaching Proxima Centauri, the nearest star at 4.24 light-years away, would take over 70,000 years. No human lifetime could come close. Even if you managed to accelerate faster, the resources, energy, and technology needed to maintain such speeds over decades are enormous. Radiation in space adds another layer to the lifetime equation, though we'll keep it simple. Outside Earth's protective magnetic field, cosmic rays and solar particle events constantly bombard spacecraft. Long-duration exposure increases cumulative risk for humans, but it also serves as a hard limit for how far humans could currently survive beyond Earth. The farther you go, the longer exposure lasts. A Mars mission lasting months already requires careful shielding. Trips to the outer planets stretch into years, and interstellar travel would last centuries, far beyond any feasible human journey today. Radiation isn't just a medical issue, it's a practical boundary that prevents humans from freely roaming the solar system at high speeds. Microgravity is another constraint, though we won't dwell on medical details. Prolonged time in zero gravity changes how the human body functions, requiring careful mission planning. Even if humans could tolerate these effects, microgravity interacts with travel duration. The longer a mission, the more prolonged the zero-gravity environment, and the more engineering needed to counteract its impact. Artificial gravity concepts, such as spinning habitats, are being explored for long missions to Mars or the Moon. But beyond that, sustaining life for decades in microgravity remains largely theoretical. Let's focus on what humans can realistically achieve today. Low Earth orbit, LEO, is well within reach. The International Space Station orbits roughly 400 kilometers above Earth. Astronauts regularly live there for months at a time. LEO trips don't require long-term acceleration or massive propulsion. Rockets like SpaceX's Crew Dragon or Russia's Soyuz can transport humans there safely. Orbital spaceflight is essentially the outer edge of what humans can sustain in a single continuous mission today. It's also where commercial spaceflight is beginning to flourish, from short-duration trips to longer stays aboard planned orbital hotels. Beyond LEO, the Moon represents the next boundary for lifetime-limited humans. It's about 384,000 kilometers from Earth. Apollo missions proved a round trip can be achieved within a single human lifespan. The astronauts left Earth, landed, explored, and returned in under 2 weeks. Modern plans, like NASA's Artemis program, aim to push this further with longer stays and more complex exploration. SpaceX and Blue Origin also envision lunar tourism, potentially allowing humans to orbit or even land on the Moon within a lifetime. These missions are constrained by logistics. Rocket speed, fuel, orbital mechanics, and human endurance all combine to define how far and how long a trip can realistically last. Mars is the next frontier, where the lifetime factor becomes sharply limiting. Current chemical rockets can reach Mars in roughly 6 to 9 months, depending on the alignment of Earth and Mars. That leaves time for astronauts to conduct exploration and return safely, potentially 2-3 years total for a round trip. This is within a human lifetime, but it represents a significant fraction of it. Extending beyond Mars becomes much trickier. A trip to Jupiter could take 2 to 3 years one way with chemical rockets, Saturn even longer. Uranus and Neptune require decades. That's where the lifetime factor really hits home. Humans may theoretically reach these worlds, but only by dedicating decades of life to travel, leaving little time for actual exploration once they arrive. Even if we imagine hypothetical propulsion, nuclear thermal, ion drives, or fusion engines, human travel beyond Mars and the asteroid belt remains constrained. Fusion engines could accelerate spacecraft faster, potentially cutting travel times to Jupiter from years to months. But this requires technologies not yet realized for human crewed missions. The faster you go, the more engineering, energy, and shielding are required. Every increase in speed is an exponential jump in complexity. Humans remain tethered to physics. We cannot instantly accelerate to thousands of kilometers per second and survive. Now let's zoom out to the outer planets and beyond, purely in terms of what a human lifetime allows. Jupiter, Saturn, Uranus, and Neptune are so far that chemical rockets or current nuclear engines make round trips impractical. Even at speeds much higher than today's spacecraft, it would take years to decades to reach these planets. That's a huge fraction of a human lifespan, meaning astronauts would spend most of their lives in transit. Beyond Neptune, the Kyper belt and objects like Pluto, Eris, and Haumea stretch millions to billions of kilometers farther. Missions to these regions are theoretically possible with advanced propulsion, but again, a single human lifetime would be almost entirely consumed by the journey. Exploration time would be minimal compared to travel time. Let's quantify the limits. Assuming humans can tolerate 10-year round trips comfortably with minimal acceleration, the furthest distance a human could travel today realistically falls somewhere in the inner solar system. Mars fits neatly within this envelope. Perhaps Venus, Mercury, or asteroid belt missions could also be feasible with optimized propulsion. Jupiter might be marginally reachable with the fastest nuclear or ion engines, but anything beyond that enters the realm of decades-long expeditions that stretch human lifespans to the limit. The lifetime factor isn't just about survival, it's about having enough time to actually explore once you arrive. NASA studies on long-duration spaceflight, particularly on the ISS, provide real-world data for this calculation. Crews spend months at a time in microgravity, and scientists monitor how radiation, isolation, and continuous life support affect humans. While these studies focus on low Earth orbit, they provide a window into the challenges of deep space missions. every year in orbit is a proxy for every year humans might spend traveling further. Life support must function flawlessly, resources must be recycled, and environmental conditions must be strictly controlled. These lessons feed directly into the question of how far a human could realistically travel today. Considering speed, distance, and lifespan together paints a clear picture. Humans are limited not just by rocket technology, but by the ticking clock of life itself. Chemical rockets can't escape the solar system quickly enough. Nuclear and ion engines extend range, but only within decades. Beyond Mars, round trips quickly become lifetime-consuming projects. The farther you try to go, the more of your life is spent in transit, and the less time remains for meaningful exploration. Even with future technologies like fusion engines or laser propulsion, reaching the stars within a human lifetime remains purely theoretical. The lifetime factor also defines the boundary between human travel and robotic exploration. While humans are limited to the inner solar system, robotic probes like Voyager, New Horizons, and the proposed Starshot missions can travel decades or centuries into deep space without biological constraints. These machines can operate far beyond what humans could physically survive, transmitting data across light years. In a sense, they are humanity's extended lifespan, exploring vast distances, while humans remain anchored by our biology. So when thinking about the maximum human reach today, Mars is the practical frontier, with the Moon and near-Earth asteroids also feasible. Beyond that, the lifetime factor dominates. Jupiter, Saturn, and outer solar system missions become decade-long undertakings, consuming nearly a full human life just to travel there. Interstellar travel is completely outside the envelope. Even the nearest stars are tens of thousands of human lifetimes away with current technology. The physics of speed, fuel, and resource management intersect with the human clock to create a very real, immutable boundary. So, how far could you actually travel into space within one lifetime? If we ask the question plainly, how far could a human travel into space in a single lifetime? The answer is surprising. The universe is vast, almost incomprehensibly so, and human life is short in comparison. Even at the speeds of our fastest spacecraft today, our reach is limited to a tiny fraction of the cosmos. But measured against current technology, orbital mechanics, and what we can safely sustain, we can give a clear, realistic answer. Let's start with the closest and easiest destinations. Low Earth orbit, LEO, sitting roughly 160 to 2,000 kilometers above Earth, is the first step. Astronauts have lived in orbit for months aboard the International Space Station, experiencing zero gravity and studying the effects of prolonged space travel. From a lifetime perspective, LEO is trivial. Any adult human today could travel there, spend weeks or months in orbit, and return without issue. The technology is mature, the logistics are well tested, and commercial space tourism companies are already offering short orbital flights. The Moon is the first real milestone beyond Earth orbit. At 384,000 kilometers away, it is roughly 30 times farther than LEO. Apollo astronauts completed round trips in under 2 weeks, proving that humans can travel to another celestial body and return within a lifetime. Modern plans like NASA's Artemis program and private missions from SpaceX and Blue Origin aim to extend stays, allowing humans to orbit or land on the Moon for weeks or months at a time. The Moon is not just reachable, it is comfortably reachable today with modern rockets and life support systems. Moving outward, Mars represents the upper boundary of practical human travel within a single lifetime with near-future technology. The planet's distance from Earth ranges between 55 and 400 million kilometers, depending on orbital alignment. Using current chemical rockets, a one-way trip takes 6 to 9 months. Add in exploration and preparation for the return journey, and a round-trip mission could last 2 to 3 years. This is fully achievable within the average human lifespan. Organizations like SpaceX and NASA are actively planning such missions. With advances in propulsion, such as nuclear thermal rockets or ion engines, travel times could decrease, making Mars trips safer and slightly more routine. Beyond Mars, however, the time required to reach other planets grows rapidly, straining the limits of human life. Beyond Mars, we enter the outer solar system, where distances increase dramatically. Jupiter lies 778 million kilometers away, Saturn about 1.4 billion kilometers, Uranus roughly 2.9 billion kilometers, and Neptune 4.5 billion kilometers. Even with the fastest realistic propulsion available today, chemical rockets or proposed nuclear engines, reaching these planets would take many years to decades. For example, the Galileo probe took 6 years to reach Jupiter, and New Horizons spent 9 years reaching Pluto. For humans traveling under lifetime constraints, these journeys are impractical. A trip to Jupiter or Saturn would consume decades, leaving little or no time for exploration upon arrival. Neptune or the Kuiper belt is effectively unreachable for humans in a single lifetime with current technology. Let's consider propulsion limits. Chemical rockets can provide sufficient velocity to reach Mars or the Moon within months, but they are far too slow for the outer planets. Nuclear thermal or ion engines could increase speeds substantially, potentially allowing human crews to reach Jupiter in under a decade. Fusion engines, if ever realized, might reduce travel to decades for the outer planets, but these technologies are still conceptual. Even at high speeds, energy requirements, radiation shielding, and life support logistics impose hard limits on how far humans can travel. Time is the ultimate limiter. Humans live on the scale of decades. Even if we ignore biological effects and focus purely on physics, the time it takes to accelerate, coast, decelerate, and explore distant destinations makes certain regions unreachable. The Moon takes days, Mars takes months, Jupiter takes years, and stars beyond our solar system take millennia. Within a single lifetime, human exploration is limited to the inner solar system, roughly as far as Mars, or in rare cases with futuristic propulsion, Jupiter. Beyond that, humans would either have to endure multi-generational ships, cryosleep, or hand over the job to robots. Radiation is another practical consideration. Outside Earth's magnetic field, humans are exposed to cosmic rays and solar radiation. On trips to the Moon or Mars, shielding and careful mission planning are sufficient to keep doses within tolerable levels. On missions to Jupiter, Saturn, or beyond, radiation exposure becomes extreme, compounding the difficulties of prolonged travel. The longer the journey, the more energy and shielding required, making these missions prohibitive for human lifespans. If we plot a visual progression of human reach within one lifetime, it looks like this: Earth orbit, the Moon, Mars, and potentially near-Earth asteroids. These are the places humans could realistically go. Beyond Mars, the outer planets, Jupiter, Saturn, Uranus, Neptune, require decades of travel. The Kuiper belt, Oort cloud, and interstellar space are entirely unreachable. In other words, our lifetime limit effectively confines human exploration to Mars and the Moon, with outer planets possible only under extremely optimistic technological advancements. Looking forward 50 to 100 years, advancements in propulsion could push this boundary outward. Nuclear fusion or even laser sail technologies might reduce travel times to the outer planets from decades to years. Mars trips could become more routine, orbital stations could host humans for years, and asteroid mining missions might become feasible. These advances could extend human reach to Jupiter or Saturn within a lifetime, but the fundamental limit remains the same. A human cannot leave the solar system and return within a normal lifespan. Interstellar distances, even to the nearest star Proxima Centauri at 4.24 light-years, are thousands of times farther than any lifetime-limited human mission could cover. The bottom line: the furthest humans could realistically travel today is the Moon and Mars, with the inner asteroid belt also achievable. Jupiter or Saturn may be possible in the future with advanced propulsion, but nothing beyond the solar system is feasible within a lifetime. Our imagination allows us to picture star systems and galactic neighborhoods, but physics, energy requirements, and the ticking clock of human life impose an unyielding boundary. Visually, if we could watch a human mission unfold from Earth, the rocket leaves the planet, quickly crossing Leo, then the Moon, and eventually approaching Mars. Beyond Mars, the distance grows exponentially. Jupiter and Saturn loom as dots in the distance, but they require decades to reach. Uranus, Neptune, and the outer solar system stretch endlessly beyond. Each step represents a massive increase in travel time, energy, and complexity. In a single lifetime, humans would only ever see the inner planets in person. Beyond that, exploration is left to probes and AI-driven spacecraft.